Sasha Tchaikovsky is going to talk about jets immediately after me. So I'm going to kind of divide my talk between accretion and jets. And part of my talk will be kind of an introduction for Sasha to go into much greater detail. So the topic is, for the whole session, accretion and jets. And here's the picture that, people have in mind. You have a black hole in the middle. Some gas comes into orbit at a large radius, and then it slowly spirals in. And as it comes in, it gets hot, it radiates. You get a very bright accretion disk. And also, in many cases, there is some ejection of material along the spin axis of the accretion disk. And that's the relativistic jet. So in the spirit of an introductory talk, I will give a little bit of the physics, because the accretion itself is interesting. Gas has to start at large radius and come to the center and fall into the black hole. And that doesn't happen easily. You need to get a few things organized. So the way to understand is to imagine that the gas is in a Keplerian orbit, and it goes through a sequence of Keplerian orbits. So as you know, just sticking to Newtonian physics, the angular momentum in a Keplerian orbit goes like square root of radius, which means initially the gas has a lot of angular momentum, and it has to lose all that angular momentum to come near the black hole. So you need a mechanism, a viscosity to remove angular momentum. And this problem was solved in 1991 when Berbis and Hawley described the magneto-rotational instability, MRI. It's a magnetic effect. It's a beautiful effect. There's no doubt at all that black hole accretion is essentially driven by MRI. The second thing is Keplerian orbits become more and more bound as they come close to the black hole. So if I think of binding energy, that is the potential energy minus the kinetic energy, the quantity is gm over 2r, which means you're getting more and more bound. It goes like 1 over r. So the gas has to keep on losing energy to reach the center. So how do you lose energy? One obvious way is through just radiation. And so whenever the gas radiates, is able to radiate and get rid of its energy, we have a very standard mode of accretion. This is called the thin accretion disk. This everybody knows because it's in all the textbooks. So here's the schematic picture. It's an object that is geometrically thin, i.e. vertical thickness is much less than radius. It's cool, so the sound speed is small compared to the Keplerian velocity. Pressure is unimportant. It rotates at Keplerian. Most important, it gives you a lot of radiation. Roughly, for typical numbers, 0.1 m dot c squared, where m dot is the mass accretion rate. So 10% efficiency. That's what we expect from a thin disk. You can also show that this model will be optically thick. So therefore, the radiation will be essentially black body. It's what's called a multi-temperature or multicolor black body. Different radii will radiate at different temperatures. And we believe that quasars and also X-ray binaries in certain states are in this particular form of accretion. So for instance, quasar spectra show something called a big blue bump. This we think is optically thick black body-like emission from a thin accretion disk. And when you look at X-ray binaries in a particular state called the soft state, X-ray binaries, as you know, are stellar mass black holes. The quasars are supermassive black holes. These guys have a nice black body-like component to the spectrum, roughly at around 2 keV for the typical system. And we think we understand these guys. They are thin accretion disks. But nature has also given us a surprise. There's no question at all from observations that when accreting black holes accrete at a low accretion rate, m dot much less than the Eddington rate, they do not have the thin accretion disk. And this is a surprise because the model itself is fine. You can use a thin accretion disk at a whole range of m dots, and you can find solutions, but nature doesn't like it. It seems to switch to something else once you're below about 1% of Eddington. And what you have then is what is called a hot accretion flow. This guy, the spectrum is completely different. There's no multicolor black body. In fact, let me show you a couple of spectra. So here is a spectrum. These are stellar mass black holes. This is the guy I showed you earlier, LMCX3. Soft state, this is all multicolor black body. This is the so-called hard state, GROJ0422. This is what the spectrum looks like, and the peak is at 100 keV. This is log of photon energy, 100 keV, whereas this fellow is at 2 keV. At 2 keV, this has nothing, right? It's just a rising power law and a peak. So this is a different state. Clearly, it's not a thin accretion disk. In fact, it has to be optically thin and very hot. We think the same thing happens also in our galactic center, which has no big blue bump at all. In fact, the spectrum peaks at submillimeter and then it just declines beyond that. Okay, so what's going on? What's going on? Again, what we think from theory is that this is a case where the gas is radiatively inefficient. And this was called advection-dominated accretion flow, ADAF. And this has been worked on a lot of people over the years. And this is kind of now the standard paradigm for this low m dot accretion. So let's look at a little bit of the physics. Why do we have these two modes of accretion? Thin accretion disk is a case of radiatively efficient accretion. So I already told you, you get about 10% of m dot c squared in the form of radiation. Usually these are very bright systems, often near Eddington luminosity. The advection-dominated accretion flow, at least the first variety that I'm talking about, these happen when the accretion rate is much below Eddington. So the accretion rate is small. In addition, they turn out to be radiatively inefficient. Basically, the gas density is so low that it's not able to radiate. So instead of radiating, the gas just holds on to all of its energy. It's coming in because MRI keeps working. So gas keeps flowing in, but it doesn't radiate. And so it gets very, very hot, virial temperature. It's no longer a thin disk. It's a big, fat, puffy disk. It's an advection dominant. Energy advection dominates, radiatively inefficient. Radiation doesn't come out much. ADAF, RIAF. More generally, Feng Yuan and I decided to call it a hot accretion flow in our review article. So the feature of this guy is radiation is much less than 0.1 m dot c squared. Now, m dot is already small for these systems, and then the radiation is a small fraction of m dot c squared. So they are very dim systems by and large. So in fact, going to the previous slide, this guy is kind of at the limit. It's a fairly bright system. This is probably at about 2 or 3% of Eddington in luminosity. This guy is kind of at the limit of what an ADAF might do in the hot state. Okay, so where do we have this ADAF? So I already told you it happens at low accretion rate. So this picture gets a schematic. The vertical axis shows the accretion rate in units of the Eddington rate. Horizontal axis shows radius in units of the Schwarzschild radius. This is just for getting a nice, a plot. The thin accretion disk appears to live basically between 1% of Eddington and 100% of Eddington. That's the range. That's the sweet spot for radiatively efficient accretion, thin accretion disk. Quasars live here. Soft state X-ray binaries live here, etc. You go below 1%, and I'm saying 1%, it's a rough number. Maybe it is 0.3%. Okay, this boundary is not very well known. But systems then switch to this hot accretion flow, which is an ADAF, advection-dominated accretion flow. And I'm going to spend a fair amount of time on this guy in the rest of my talk. And the thing that's interesting about this mode of accretion is it seems to be a beautiful system for making jets. Relativistic jets form quite easily and spontaneously whenever you go into this regime of accretion. So this is the hot accretion mode. Now, if you go above Eddington, there is another kind of accretion, super Eddington accretion. It's also called the slim disk, first described by Abramovich et al. In '88. Now, that's also an ADAF for a totally different reason. It turns out that here, there is too much gas, and even though the gas is radiating, the radiation cannot escape. So again, energy is bottled up. And because it's bottled up, the system becomes an ADAF, advection dominated. It becomes thick, puffy. In fact, in a lot of respects, this regime and this regime are quite similar in the physics of the accretion and in the physics of the jets. I will say a little bit about this right at the end of my talk, if there is time. I'm going to spend more on this lower mode just because, Sasha will also be talking about this, and there'll be a nice continuity between the two talks. So for our purposes here, these two guys, bottom and top, good for jets. Boundaries are approximately shown here. This guy in the middle, I personally don't know whether it's good for jets or not from a theory point of view. From observations, we know specifically for X-ray binaries, when they go into the soft state here, their jet usually shuts off. They will have a jet here. Then when they make the transition, they have one burst of jet emission, and then they become very quiet, no jet. So there's a hint from observations that a thin accretion disk normally cannot support a jet. I do not have a theoretical explanation or proof of why this might happen. Okay, there are guesses, and maybe Sasha will talk about this. I won't say too much about this. I'm just going to put the question mark and leave it there. Okay, so now let's continue on to jets, the main part of my talk. First thing I want to say is you need to do numerical simulations. I mean, you can study jets beautifully with theory, but it'll always be an incomplete story because you can only look at the jet, or you can only look at the accretion. The reason is accretion is coming along the radial direction. The jet is going along the pole in the z-axis, and it's very hard to do theory in multiple dimensions. We can do nice one-dimensional theories, but once you go to multi-dimensions, at least, it's not easy any longer. Simulations, you can do any number of dimensions, 2-dimensional, 3-dimensional, whatever, no problem. So the multi-dimensional physics is very natural in simulations. Magnetic fields we know are important. They are important for the accretion through the MRI. And as I'll show you now, the jets are also driven by magnetic fields. So you need to include magnetic fields. It's not just hydrodynamics, it's MHD that makes it harder. There is turbulence. The same MRI produces turbulence. You need to deal with that. And of course, you want to do general relativity. It's not Newtonian physics any longer. Kerr metric, it all gets quite hard. On the computer, you just put in all the equations and then you let it go. So I'm going to show one movie as an example. People have been doing this now for 20 years. This one is from Chatterjee's paper 2019. So this is a typical simulation. The black hole is here, right in the middle. You start with a torus of gas, which is orbiting around the black hole. So this is the vertical axis is the angular momentum axis of the torus. We are just seeing a slice, and the thing is axisymmetric to start with. It's kind of going around the black hole. All these lines are magnetic field lines. And basically, when I start the movie, you will see this guy evolving, and you can see, I'll just stop it here. MRI is already making it all very turbulent here. You can see the field lines are all twisted up. MRI also causes accretion, gas is coming in. It also brings the magnetic field. You get a nice aligned, organized magnetic field along the pole. And this is where the jet is going. The jet is carrying away energy along these polar flows. Accretion is coming along the radial direction. So you can continue to see the movie. So this just shows now an expanded view. So the torus is right here in the middle. Now we have gone to a much larger scale. Initially, what I showed was just a few tens of Schwarzschild radii. Now we are going up to 10 to the 5 Schwarzschild radii. So the jet is beautifully organized and goes on forever. 10 to the 5 on the computer, 10 to the 8 or 10 to the 9 in nature. It's very interesting. And the magnetic field keeps it organized. So it's all magnetic. Here's another view of this guy. This is now in 3D. Come on, I want to go to the next slide. Good. This is now in 3D. Same simulation. So there is the torus. This is the jet. And you can just see once again how this thing works. It's just happily going away. And, again, just a pretty movie, just to show you. I mean, this is real simulation. It's not an artist's impression, right? It's a real simulation. Real quantities are being shown. And once again, the scale of this thing is 10 to the 5 gravitational radii. Okay. So this is something that happens with very little trouble, actually. Anytime you simulate an ADAF, radiatively inefficient accretion, it produces these jets. We also understand the physics. The physics, at least in these simulated jets, is definitely consistent with energy extraction from the black hole, specifically from the black hole spin. So here is the spin parameter A star, which is A over m. It's a measure of angular momentum per mass. And this is the number that, if you remember, can go up to 1. 0 means non-spinning, 1 means maximum spin. That's the extreme Kerr black hole. And I will actually consider spin going from -1 to 1. -1 means the black hole is spinning in the opposite direction as the accretion disk. It's a maximal spinning black hole, but in the opposite direction. +1 means it's going in the same direction. 0 means the black hole is not spinning. And just from simple dimensional analysis, with some some physics going into it, you can show that the power that you can expect in this jet scales something like this: phi squared A star squared. So it goes like the square of the spin parameter. If you don't have spin, you don't get jet power, not by this mechanism at least. And it goes as a square. So this can go between 0 and 1. It also depends on this quantity, which is the magnetic flux, the organized magnetic flux around the black hole. Gauss times centimeter squared magnetic flux, and then you square it. So you need magnetic field. The more field you have, the more jet power you get. Okay. I'm going to show you how this mechanism works. Why is the spin important? Basically, spin induces frame dragging in the space-time around the black hole. And because of frame dragging and the interaction with the magnetic field, it kind of naturally produces outflowing energy. So this movie, which I've taken from an old paper by Semenov et al., 2004, shows a spinning black hole. So this is the horizon of the black hole. This is one magnetic field line, which is just falling in, accreting onto the black hole, but it doesn't fall in directly. Because of the spin of the black hole, space is dragged around the black hole, and the field line comes in front, goes behind the black hole, gets dragged round and round and round. So the dragging of space-time takes my straight field line and twists it up. It just goes round and round and round, and you can see what happens. The net result is, even though I started with a straight field line, it becomes a corkscrew, a helix. And that helix is moving out along the two axes. That's your jet. That moving helix is carrying energy, also angular momentum, but it's carrying energy, and it's that energy which then comes out at very large distances as your relativistic jet. So end of the day, it's a purely relativistic effect. It's frame dragging, which is coming from general relativity, and that is why the black holes, a spinning black hole, is able to produce relativistic jets. Okay, good. That's the physical picture. The way the scaling works, I've already shown you. This is how the jet power goes. So what are the things we need if you want to make a strong jet? You need an organized magnetic field. I showed one field line. One field line won't produce much power. But if you can put a whole bundle of field lines around the black hole, and then you make the black hole spin, you take that whole bundle and you're twisting it up all the time, and that twist sends off helical pattern carrying away energy. And the lesson we have learned from simulations is, when you have a geometrically thick ADAF system, This seems to happen without any difficulty at all. You need some magnetic fields, you need the spin of the black hole, and then almost always it seems to produce these jets. And I think Sasha may say more about this, how almost inevitable it seems that you will get jets from these systems. Now, why is this ADAF so good? And I'm assuming that a thin disk is not good, even though I can't prove that that's the case. But the ADAF seems to be particularly good because it is able to bring the magnetic field down to the black hole. If you start with magnetic field anywhere, you have a thick disk, that field happily comes down to the black hole, dragged by the gas, which is good for making a jet. Also, I think once the jet is formed, the field lines are collimated because there's this big fat disk. The field can't go anywhere else. It's collimated along the funnel, and that maybe helps. So these are all guesses, but the fact is simulations produce beautiful jets. Okay, but how powerful can you make the jet? Okay, so you've got a nice formula here. So you look at this formula, and it says, I can increase the spin. The more spin I have, the more power I can get in the jet. But you can only go up to 1, right? It's a limit. But there is the second guy, the magnetic flux. Maybe you can put arbitrarily large magnetic flux and get arbitrarily large power in the jet. It turns out that is not the case. There is also a limit. Just like spin has a limit, there is a limit to how much magnetic flux you can put around the black hole. Because the more magnetic field you push around the black hole, the more pressure it has, and it pushes back. And it says to the gas, don't come. It pushes the gas away, but it's the gas that's keeping the magnetic field in after all. So what happens is you can keep on pushing magnetic field, and then you reach an equilibrium, what is called a MAD disk, or magnetically arrested disk. So this is a system in which there's a lot of magnetic field, not infinite amount, lot of magnetic field around the black hole. The field wants to escape. If you didn't have any accretion disk, it will go off to infinity. Because of the disk, the field cannot escape. So the disk is pushing in, the field is pushing out, and you reach this kind of quasi-equilibrium where the disk is kind of disrupted, and then it continues to accrete not in axisymmetric form, but through streams and blobs, etc. But this is kind of a natural end state. If you keep on pushing in field, the system will reach the state and it will stop. And the place where it stops is when this dimensionless number, magnetic flux divided by something that depends on m dot, is equal to 50. Okay. Now, why 50? I'm not going to try and explain. Actually, I don't fully understand. But the point is there is a maximum, and that maximum is the configuration which is called a MAD system, magnetically arrested disk. Corresponding to that, it turns out that you can get a maximum jet power, maybe up to 1.5 m dot c squared. That is to say, if you push A star to the limit and you put phi also to the limit, this 50, you can get a power of 1.5 m dot c squared, which of course is a hell of a lot more than what a thin disk can produce, right? Thin disk can give you 10% efficiency, 0.1 m dot c squared. A jet can have much more efficiency. As Tchaikovsky showed in 2011, he showed a simulation with 140% efficiency. Now, I don't know what the actual limit is. It's probably 150 or 200%. There is a limit, but it's a lot, okay? Much more even than all the rest mass energy in the accretion flow. And the reason for that is this is not really accretion energy that is going into the jet. It is black hole spin energy going through the so-called Penrose process, frame dragging magnetic fields. Okay. So, next lesson from all of this. If the black hole spin is powering the jet, how is it working? Essentially, what's happening is the black hole spins and it, as I showed, drags the field around and carries away energy. But in that process, it also carries away angular momentum because the interaction is through the spin of the black hole. So while the jet is carrying away energy, because it's also carrying away angular momentum, your black hole has to spin down. Okay, so this is, I think, the next lesson here. Pretty much all of these ADAF systems, when they go into the mad state and they produce these powerful jets, the black hole is spinning down, which is a very different situation from a thin accretion disk. Okay, so black hole spins down. Here, for instance, is a plot showing as a function of spin parameter how the spin parameter of the black hole changes. So this is some dimensionless number. How much change do you get in A star for a certain fractional change in the rest mass that you add to the black hole? Positive means you're spinning up the black hole. Negative means you're spinning down. And you can see this side is all co-rotating disks, all the way from 0 to 1. You're always spinning down the black hole. So you can start with a very rapidly spinning black hole. It's wonderful for making a very powerful jet. Okay, but it won't last forever. Even while that jet is, coming out, it's constantly slowing down the black hole. The black hole will become slower and slower. The jet will become less and less powerful. And if it go on for too long, your spin will come close to 0, and then you'll hardly have any jet. Okay, so these have to be somewhat short-lived phases, these powerful jets. If you had a thin accretion disk, on the other hand, this everybody knows, a thin accretion disk spins up a black hole. And I'm assuming that the thin disk is not mad, it doesn't have a jet or whatever. This is the original Novikov-Thorne's thin disk. It'll always spin up the black hole. But our ADAFs are the opposite. They spin down the black hole. Okay. Another interesting point, you can already see that, the counter-rotating disks behave differently. It's not a mirror symmetric figure here. And when you look at other parameters, you can actually see that counter-rotating disks are not the best systems for jets or power or any of those things. The co-rotating disks are the best. And here is a plot which shows efficiency, jet power in units of m dot c squared as a function of spin. Co-rotating disks are on this side. A co-rotating disk, very rapidly spinning black hole, amazing. You can get more than 100% efficiency in the jet, and I think it goes up to 150 or 200%. You can have a maximally spinning black hole, but counter-rotating, you get only 20%. Okay, it's just much less efficient, and primarily the reason is that this magnetic flux itself is not so high. You can go up to 50 or 60 for co-rotating. It's much less. It's only about 20 or 25. And because it goes like the square of this parameter, the jet power is down. So this, I think, if you look at a system and you see something extraordinarily powerful, chances are that it's a co-rotating disk. I don't know what's the story with tilted disks in between. This will be studied, I guess, pretty soon in the future. I don't have time to talk about radiation because I'm running out of time. Everything I told you was just mechanical energy so far, right? Just magnetic energy, kinetic energy, stuff flowing out. Somehow it has to become radiation. So that's what we observe. Somehow you have to heat the gas, and then you also have to produce non-thermal electrons. So people have done some very nice work on this. Magnetic reconnection will do stuff. Instabilities will do stuff. I'll just run a movie here to show you what instabilities do. Instabilities basically occur. See, this is the jet that's going out. Occur in the boundary between the jet and the disk. It's a well-known instability. It's called I think the pinch instability, or it's related to Kelvin-Helmholtz. They're all the same, similar thing. And this is probably where you produce the heat and the radiation, and maybe even non-thermal particles. And if you look at the image of M87, you can see that it is an edge-brightened jet. It's probably because of something like this. Very early days, people don't really know enough to say any of this with confidence. I ran out of time, but I did want to say 2 minutes, if the chairperson will allow, two minutes about the second mode of accretion, ADAFs in super Eddington accretion. I'll just say this quickly in words. That mode also produces jets, almost unavoidable, provided you can reach the MAD limit. All the same reasons, I think, make MAD very natural there. In our simulations, we have seen up to 200% efficiency in these systems. It's very similar behavior as I won't show the movie. So here is a plot showing that this 5 parameter can go up to 50, just like in the lower ADAF systems. This is efficiency PJet. You can go up to 2, which is like 200%. These are somewhat uncertain numbers. But the point is, almost all the lessons we have learned at low m dot hot accretion appear to be equally valid in super Eddington accretion. So the relevance of this for real systems is yet to be worked out. But there's, I think, a huge interesting field out there. So let me stop here. Here's my summary. Black hole accretion has got 2 primary modes that we understand: radiatively efficient, advection dominated. Next thing we have understood is advection dominated seems to be a very natural scenario for producing relativistic jets. And they are especially efficient when they go into this magnetic arrested disk mode, MAD. The jet power has got simple scalings, depends on only 2 parameters, spin and black hole magnetic flux. And the simulations are just telling us more and more. And I think we can wait for Tchaikovsky's talk to get much more details on this kind of accretion. So I'm going to stop at this point. Okay, Shokofe, I'll stop here. Shall I stop sharing?
Yeah, I don't know, maybe people wants to see the slides when ask questions.
Yeah, okay.
Thank you very much. It was a very great talk, as usual. And is there any questions? If you have a question, please raise a hand in the reactions part. Okay, Aoife, please ask your questions.
Yeah, thank you for this wonderful talk. I have a question about the time scale. You mentioned the spin down for the MAD disk. Can you say something about this, the time scale on which this happens?
Yeah, better than time scale. I can tell you what happens as a function of how much mass you add. So in terms of this spin down, let me see if I can find the. Okay, so this is so let's imagine I've got a very rapidly spinning black hole, spin of 0.9 or 0.95 or 1 or something. This number here says it's -10. And all this means is the following. Let's say I've got a rapidly spinning black hole with this spin. And let's say I add 1% mass to it via an ADAF in this MAD accretion disk state. If I add 1%, the spin will reduce by 10%. So spin 1 will become spin 0.9, or 0.9 will become 0.8. If I add 3%, it will change by 0.3. So that is the amount of spin down that you have. How long that takes depends on the rate at which you're accreting mass. Typically, these hot accretion flows have, in Eddington units, less than 10 to the -2. So let's say 10 to the -2, 10 to the -3. If my system accretes at that rate, I would say that it'll probably spin down substantially in about 10 to the 9 years or even less. Okay, so that's the number, 10 to the 9, maybe even few 10 to the 8. But if it's accreting at 10 to the -8 Eddington, which is probably what our galactic center is doing, then, even the age of the universe, nothing will happen because, this is not adding much mass.
Okay, thank you very much. Does this already include the upspin of the black hole due to the accretion of the mass? I mean, if you accrete, you also upspin.
This is the net effect.
Okay.
You are, of course, adding some angular momentum from the accreting gas. Not as much as for a thin disk. This is less because this guy is not rotating Keplerian. It's actually rotating slowly, but you're right. There is some angular momentum just from the gas flowing in, but what flows out through the magnetic field is so much more that the net effect is a huge spin down. So yeah, it's a very good question you've asked. So this is the total. This is not looking at only one part of the answer. This is the net effect of all the contributions, what goes in, what goes out, etc. Huge amount of spin down.
Okay, thank you very much.
Okay, John Wallace, can you ask your questions, please?
Right, yeah. So you said that you need an ordered magnetic field to get this for this jet production mechanism, but according to the MRI instability and also to the simulations that you showed, it seemed like the magnetic fields were quite disordered. So are these two things really consistent with each other?
This is, I think, a very good question. We do start our simulations with zero net vertical field. These are loops, okay? So they are zero net vertical field, but still, you know, they start with a fairly organized structure. And so you get organized magnetic field rather, you know, easily from our simulations. I have a feeling Sasha will talk about what if you don't have any vertical field at all? If you start with just toroidal field or something else, I think he's going to show, if not, I will tell you because he has published this stuff, he and Matthew Liska and others, that it doesn't seem to matter. Even if you start with a really unpromising initial magnetic field configuration, still the system seems to go naturally to an organized vertical field and a powerful jet. But let's wait for Sasha's talk.
Okay, thank you. The next questions, Professor Brandt, please.
Just have a question, Ramesh, coming from an observational point of view. I would do a lot of work on quasars. I know there are many examples of luminous radio loud quasars that certainly seem to be launching jets. You kind of dismissed the capability of radiatively efficient systems, at least non-super Eddington ones perhaps, to be launching jets. Do you have any further thoughts on that?
There's a question mark here. And, you know, that really means I don't know the answer, okay? I really don't know whether these guys can or cannot produce jets. And the quasars, many of them, I think, live here. I do know that stellar mass black holes stop producing jets when they go in here. So just by analogy, one thinks quasars shouldn't have jets either, and maybe your radio quiet quasars are all living here. You ask a really good question. What are all these radio loud, powerful jet, but bright luminous quasars? I would like to think that they are near this boundary, that they're close to Eddington or a little bit over Eddington, because I know that I can definitely produce jets up here. I cannot tell you that the jets disappear here in simulation. We have tried and it doesn't seem to happen on the computer. They keep producing jets down here. I'm hoping that Sasha will have the final word on this. I don't know the answer.
Okay. I will note, of course, that some of these radio loud quasars have been reverberation mapped in an attempt to measure their black hole masses and their Eddington ratios. They don't all seem to be super Eddington. Clearly, the observations might be misleading somehow, but it's a puzzling thing.
It is a definite puzzle. Yeah, I think there is a great scope for better understanding of how this regime relates to jets. I feel that we are beginning to get a handle on these two regimes. But this one is still, I think it awaits a lot of clarification.
Okay, thanks a lot.
Okay, and the last questions with Tushar Mandal, please.
Hi, Ramesh. So when you were talking about that magnetic flux with respect to that accretion rate, so as you keep increasing that accretion rate in that super Eddington regime, so is it that magnetic field is saturated because of the diffusion time scale less? at that MAD region, or something else is happening there?
It's hard to answer this question beyond the qualitative description I gave. Essentially, what's happening is, if you don't have a lot of magnetic flux around the black hole, and let us say your disk is threaded with magnetic field, when the gas accretes, it will pull the magnetic field in, it will drag it in, and all that flux, just through flux freezing, will get to the center and it will accumulate here.
Yes.
But pure flux freezing will tell you that it will keep on accumulating without any limit. But in practice, what happens is, once you reach this mad limit, you get some instabilities in the disk. And using the word you use, diffusion, effectively that instability, which is interchange instability, behaves like a diffusion. It allows the magnetic flux to diffuse back through the accretion disk. So it's a kind of a competition between diffusion via an instability and accretion via flux freezing. So you reach this kind of a balance, an equilibrium. It's a nonlinear phenomenon. And that's when phi no longer increases. That is my understanding, okay? Definitely the instability exists. You can work out the theory of this instability, the interchange instability. And on the computer, that seems to be operating, except that the accretion is not through blobs. Actually, it's through streams, nice spiral streams. And maybe we'll see a picture of that in Sasha's talk. If not, you can see that in papers. So yeah, it is diffusion, but it's a competition. Nonlinear turbulent diffusion versus flux freezing advection.
Right. So in other words, that in super Eddington accretion, magnetic field is not reaching up to superposition, that things, right? Because of this diffusion.
Well, it's reaching whatever maximum is allowed.
Okay.
About some recent work in my group assessing the nature of the X-ray emission from typical radio loud quasars. My screen back here. And our focus today is going to be on the energetically dominant nuclear X-ray emission, the small scale emission, not on the extended and resolved X-ray jets. And we are also going to be aiming to determine the nature of the X-ray emission from the general typical majority members of the population. We certainly appreciate that there are exceptional outliers, and I will comment on them further later. The work that I'll be describing has been led by an excellent Penn State graduate student, Shifu Zhu, shown here. And I've made substantial contributions, as has John Timlin, a good Penn State postdoctoral researcher. And it has been known since the 1980s that radio loud quasars show excess X-ray emission compared to matched radio quiet quasars. And the amount of excess X-ray emission is large. It's about a factor of 3 on average, so that it generally dominates the X-ray power output from these systems. And the nature of this excess X-ray emission has been mysterious. Since the 1980s, the standard adopted picture has been that this nuclear X-ray emission largely arises from the jets themselves, that there is some kind of non-thermal synchrotron self-Compton or inverse Compton emission, non-thermal inverse Compton emission on small scales that produces this excess X-ray emission. Key early papers discussing this were papers back in the 1980s by Zamarani, by Diana Worrell, by Wilkes and Elvis, and so on. And this standard picture was sensibly based upon luminosity correlation studies, as well as X-ray spectral studies. But the early data were fairly limited, and we believe now, as I will describe, had some significant biases. And so based on extensive analyses of new high-quality samples that I'll be describing, we now actually believe that the nuclear X-ray emission from typical radio loud quasars largely rises from the corona in these systems. The corona that dominates the X-ray emission from the radio quiet systems is still present in the radio loud systems, and in fact is dominating this nuclear X-ray emission for the typical systems. There are exceptions, as I mentioned. These are fairly rare. Blazars clearly are jet dominated, as are highly radioluminous flat spectrum radio loud quasars, but the typical systems are coronal dominated. And today I'll give a few highlights of the work. So as I had mentioned, first I will start with a brief description of our sample. So we work with Sloan Digital Sky Survey quasars from data release 14. And these are optically selected radio-loud quasars from a large area of the sky. We've carefully analyzed the corresponding radio data to select out the radio quiet systems. And we then select those with sensitive Chandra or XMM Newton coverage. And because there are enormous Chandra and XMM archives available now, we can get a large number of such systems. In fact, we have now a sample of 729 well-characterized radio-loud quasars spanning a wide range of redshift. These are mostly serendipitously X-ray covered systems. This minimizes biases. The majority of them are X-ray detected. They have quality radio slope measurements for the majority of the systems. That's very important for determining their nature, as I'll describe. We have multi-wavelength spectral energy distributions for all these systems from a variety of surveys. And we also have, of course, the SDSS spectra. And we use appropriate subsets of these 729 radio-loud quasars for the various studies that I'll be describing. Here is just a quick plot of the luminosity redshift diagram for our object. They span a wide range of redshift, and these are typically luminous radio-loud quasars. So I'll start with a paper that we've finished last year looking at X-ray ultraviolet radioluminosity correlations among these systems. And it has been known for a long time that radio quiet quasars follow a long established correlation between the X-ray emission associated with the corona and the ultraviolet emission associated with the disk. And you can see that here. Here is X-ray luminosity. Here's ultraviolet optical luminosity along this axis. The radio quiet quasars are shown here. This is the long known radio quiet quasar relation. It's a sublinear relation between the X-ray and the ultraviolet luminosities with that power law slope. Now, the notable thing is when we analyze our radio loud quasars, we find actually some notable similarities to the radio quiet systems. In particular, the steep spectrum radio loud quasars follow almost the same correlation quantitatively, and the error bars are now pretty small, as do the radio quiet quasars, just offset to a higher level of normalization. That indicates that the steep spectrum radio loud quasars may in fact have coronal X-rays as well. When we look at flat spectrum radio loud quasars as a class, they show a somewhat steeper correlation. You can see that here. And this suggests that they likely do have some jet contributions to their X-ray emission, at least sometimes. We have broken this up into bins of radio loudness. And we find for the steep spectrum radio loud quasars that the normalization of that relation between X-ray and ultraviolet luminosity smoothly increases with the radio loudness, here color-coded, while always retaining, to the best of our ability to measure it, the same slope that the radio quiet quasars have. So it appears, at least at first inspection, that the steep spectrum radio loud quasars may have a radio quiet quasar-like coronal emission, but with a jet-linked X-ray volume control, such that as you dial up the jet, the corona becomes more and more powerful correspondingly. That is, there's a corona-jet connection, as is often found for the stellar mass black hole systems. Furthermore, then if you look at the flat spectrum radio loud quasar shown here in this bottom panel, they, at low radio loudness values, have a slope that again is similar to that of the radio quiet quasars. But as you dial up the radio loudness of these systems, they progressively depart from the radio quiet quasar relation slope, indicating that as you go to higher levels of radio loudness, there is an additional X-ray component likely associated with a jet coming into play. So these are the systems where the jets are probably important. For the other ones, there's not much evidence that there is such an important contribution from the jets. We have also performed a large-scale statistical model selection aiming to compare critically the different possible interpretations. It's a highly involved analysis. I'm not going to go through it in all details. You can see the 2020 paper for details. But briefly, we utilize the Akaike and Bayesian information criteria to try to assess which models actually best describe the data. And I will just tell you, the data generally prefer the coronal scenario that I described with the corona jet connection for the steep spectrum radio loud quasars and for the radio loud quasar population in general. However, there does appear to be a distinct jet X-ray component likely be important for a small portion of the flat spectrum radio loud quasars. So the overall picture emerging from our luminosity correlation studies is the following. As you dial up the importance of a jet in these systems, the corona, again, a magnetic structure just like the jets,
quite plausibly related to the jets, seems to grow in its intensity as well, such that the corona of radio loud quasars become X-ray brighter with increasing jet power. That's the overall picture emerging from the luminosity correlation analyses. Now, we have investigated this further in a recent paper where we look at the X-ray spectral and variability properties of these typical radio loud quasars. And we find a number of notable results here. First of all, if you just look at the basic power law X-ray spectral slopes of these systems, we find that the median power law X-ray spectral slope of radio loud quasars, shown here in the top panel versus signal to noise ratio of the data, is actually close to that of matched radio quiet quasar, shown down here in the bottom panel. This result that we get for the radio loud quasars is actually considerably steeper than for past radio loud quasar samples having X-ray spectra. We believe this is because many of the past samples were small and heterogeneous with an overrepresentation of radio selective flat spectrum radio loud quasars, the highly beamed objects. And so the point here is that we have now substantially eroded the previously claimed differences in the X-ray spectral properties between radio loud and radio quiet quasars. Moreover, we find no strong correlations of this power law continuum slope with radio loudness or with the X-ray excess compared to that of a radio quiet quasar. Again, supporting that there isn't some strong change coming into play as you dial up these parameters in terms of the X-ray generation mechanism. We have also looked at X-ray reflection features. And here the results are quite interesting. The idea basically is the following. If X-ray emission from the radio loud quasars is largely indeed from jets, from beamed emission associated with the jets, then reflection signatures, X-ray reflection signatures should be weak. The idea being that the beam jet continuum will dilute away the X-ray reflection features. However, when we perform a stacking analysis of 216 radio loud quasars, we find clearly detected iron K alpha emission with a total equivalent width of about 190 electron volts. We have, as I mentioned, performed a self-consistent analysis of radio quiet quasars, and we find that the strength of the iron K alpha emission is comparable for the radio loud systems as for the radio quiet systems. They're statistically consistent. We also find suggestive evidence for a Compton reflection hump, and all of this is exactly as expected if the origin of the X-ray emission is coronal in nature rather than being a beam jet component. And I will also mention that we've looked at the long-term X-ray variability for 105 radio loud quasars, and that also supports a coronal origin of the X-ray emission. Finally, I will talk about our third analysis. Here we have looked at the correlation between alpha OX, that's the optical to X-ray power law spectral slope, and the strength of the helium-2 emission. And this is a paper that's recently appeared led by John Timlin. And here's the basic idea. Here we plot the X-ray to optical flux ratio, alpha OX, versus the log of the helium-2 equivalent width. And the helium-2 equivalent width is a useful tracer of the extreme ultraviolet continuum at 4+ Rydbergs, because that's where helium-2 is made from. And the point is that if you look at radio quiet quasars, which are the light blue data points here, and you look at many radio loud quasars, for example, the purple and the yellow data points, they actually appear to follow the same relation. Now, why is that interesting? Well, the point here is that for most radio loud quasars, when the X-rays get brighter, the unbeamed extreme ultraviolet responsible for making the helium-2 emission gets correspondingly brighter so as to maintain the location of the radio loud quasars on the same relation as for the radio quiet systems. The exception is for the highly radioluminous flat spectrum radio loud quasars, these black data points, which clearly lie above the relation. And so the idea is that these may have beamed jet X-rays that elevate the X-ray emission without also correspondingly elevating the helium-2, but for the majority of radio loud quasars, that does not seem to be the case. Okay, so I will end just by mentioning a few additional implications of our results. First of all, our results improve the unification of quasars and black hole X-ray binaries. Black hole X-ray binaries, in terms of their X-ray spectra, generally appear to have corona-dominated X-ray emission, even when they're launching jets, when they move through the hardness intensity diagram. It appears that most of the time, the hard X-ray emission from these systems is still coronal-dominated. It was puzzling that the supermassive black hole systems did not also appear to be coronal-dominated. The suggestion, again, had been previously that it was a jet-dominated X-ray spectrum. Our results, which actually argue against that and push toward a coronal origin, actually improves the parallelism between the stellar mass and the supermassive black hole systems. Moreover, because we now believe we understand the emission process properly for the radio loud quasar systems, we have tried to make a kind of hardness intensity diagram for the supermassive black hole systems. We have already heard mentioned in some of the previous talks that there is a well-known diagram that is used to diagnose stellar mass black hole systems, the hardness intensity diagram. And they move through this diagram in an interesting way. And in some parts of the diagram, they launch jets. In other parts, they do not launch jets. And this has been a useful diagnostic for understanding these systems. We have now attempted to make an analogous diagram for the quasar shown here on the left. Here we use the ultraviolet emission as the intensity, because we're trying to measure the power from the disk correspondingly to what is typically measured here. And then we use alpha OX to measure the hardness of the systems. And you can see that radio quiet quasars lie down here in this part of the diagram, following this well-known, again, alpha OX ultraviolet luminosity relation. And then as you dial up the radio loudness, the tracks just remain parallel, scaling upward and upward as you move to higher radio loudness values. So that we now believe we're starting to construct a kind of analogy to the hardness intensity diagram for supermassive black hole systems. And we actually find that we can actually identify the jet line with the alpha OX LUV relation. So that gives another interpretation of this well-known relation. And then finally, I won't have time to go into all the technical points, but we also are finding some evidence observationally now that indeed the black hole spin alone probably does not control quasar radio loudness. And indeed that magnetic flux topology, as we've heard from the previous talks, is also likely critical. We are finding some observational evidence for that. And I will refer you to these papers for more details on those findings. Thank you.
Thank you very much. And thank you that you were on time completely. Thank you. Is there any questions? Okay, please, Professor Narayan.
Yeah, so Neil, that was very interesting stuff. In your sample, do you also know the Eddington ratios? And does that play any role at all in any of these correlations?
Yes. Okay. So we do have measures of Eddington ratios. I'll go back to this diagram here. However, the Eddington ratios that we have available presently for these systems are the kind of single epoch black hole mass estimate derivations. In other words, these objects have not on a large scale been systematically reverberation mapped so that we have a direct measurement of the black hole mass. Rather, we are using the typical well-known scaling relations to estimate the black hole masses. And yes, we do. When you use those relations, which you can trust or not as you think best, we find that they are at moderate Eddington ratios of a few tenths, typically, something like that. So that's our best estimate of the Eddington ratios. Now, we have tried to look at some relations with Eddington ratio. For example, we tried to look at correlations of the X-ray spectral properties with Eddington ratio. And unfortunately, due to the individual measurement errors right now, we are not able to establish, for example, that radio loud quasars follow the well-known relation between power law, X-ray spectral slope, and Eddington ratio that is well established for the radio quiet quasar systems. That is something that we hope to do in the future with better X-ray observations. So is that addressing your question, Ramesh?
Yeah. Thank you. Right.
Okay. Yeah. So we certainly have that in mind. We are working on that, but it is a challenging thing because I would personally, as an observer, be a lot more comfortable if we had some more reliable reverberation mapping data for these objects, and I would also like better X-ray data, and we're pushing toward getting that now.
Thank you very much. And is there any other questions? Okay, let's move to the next speaker, and I will ask Audrey to continue the session. Thank you.
Okay, then the next speaker will be Kotaro Moriyama, and he would discuss about the measurement of black hole spin with the Event Horizon Telescope, theory of relative echoes, and VLBI observations. So please,
Yes. So can you see my screen and can you hear me?
Yeah, we can hear you and we can see your screen perfectly.
Thank you so much for the introduction. So we would like to talk about our method for black hole spin measurement based on the Event Horizon Telescope. So our research interest is the strong gravitational field in the vicinity of the black hole. The observational proof of the black hole spacetime directly connect to the test of the general relativity theory. The general relativity predicts that the black hole spacetime is uniquely determined by the black hole mass and spin. Here, the black hole mass can be relatively accurately measured by the observation of motion of stars and gas around the black hole. But black hole spin measurement is not easy for us because it directly connects to the radiation phenomena in the vicinity of the black hole. So we need to carefully consider the general relativistic effect and extract from the complex radiation from the region. EHT observation provides a great result in the vicinity of the black hole. For example, if we focus on the M87, we obtain the radiation phenomena in the vicinity of the black hole and its polarization profile recently. So Event Horizon Telescope enable us to obtain some new method for black hole spin measurement. Our main target is the black hole image of Sagittarius A star, which is located at the galactic center of our galaxy. So this black hole have one of the largest size of apparent diameter of the event horizon, in addition to M87. And importantly, it have a quite rapid time variability whose characteristic rotation period is about 30 minutes to 15 minutes. So this target is quite important for extracting the black hole spin information from such a rapid time variability, which is predicted from the accretion flow in the vicinity of the black hole. So our main focus is intermittently falling to the gas cloud, which is intermittently falling to the black hole from the accretion disk. So we carefully check the relativistic radiation phenomena step by step. So we start from the fundamental and simplest model and move on to the more realistic case by mitigating each assumptions. First, simplest case is we simply put the simple gas cloud structure and infold to the black hole with keeping with the angular velocity and its energy. So if we focus on such a simple case, we found the phenomenon characteristic radiation time echo between the two types of the radiation component. If we focus on the right panel, we can see the distant observer extracts first the blue photon component, which actually reaches to the observer. But after that, we obtain the secondary component, which rotates around the black hole and then reaches to the distant observer. So this is we identified these phenomena and focus on the radiative property of this phenomena and extract and distinguish with black hole spin indicators. So this is a light curve information and simulated movie. And if we focus on the light curve information, the light curve is composed of direct and secondary component, as shown in the previous schematic picture. And the time scale between direct and secondary component is consistent with photon rotation around the black hole. In this case, we shows the spin equals 0.9 and the viewing angle equals 75. And also the gas cloud assumed to fall from the marginally stable orbit from located as the disk component. And we only consider the single gas cloud infalling case. But if we expand our methodology to more realistic case, we need to mitigate each assumption step by step. So, for example, if we change the spin information, we can still change the characteristic radiation echo. So left panel shows a spin dependency of the echo right curve, and from bottom to top, the black hole spin increase, and the time interval between direct and secondary component uniquely decreases due to the decrease of the photon rotation circular orbit. So, right panel shows the time interval between direct and secondary component and the characteristic photon period coming from around the secondary photon radius. So these two characteristic time scale is consistent to each other, and spin uncertainty does not change our result. But how about the viewing angle and the accretion flow model? So this previous result is depend on the gas cloud model assumption, and also viewing angle and initial velocity assumptions. So we show 6 panel for the model uncertainties and viewing angle and the different kind of initial velocity uncertainties. So top panels shows the model, the gas cloud structure uncertainty, but the time scale bit of the echoes does not significantly affected by the underground assumption of the gas cloud model. And the viewing angle shown in the left bottom panel does not also change the time interval between each two peaks. And if we change the velocity based on the present GRMHD velocity field, the echo interval does not significantly change. So our model does not change based on the model assumption, but this is based on the single gas cloud model, and we need to check the plenty number of the gas cloud situation, like a real observational case. So left panel shows we randomly and plenty number of the gas cloud are falling to the black hole, and investigates light variability by using the latest EHT UV coverage. So right panel shows characteristic UV coverage, which will be accomplished during 2017 to 2022. So based on the systematic synthetic observation for such a complex and plenty number of the gas cloud, we check the possibility for detecting such a time radiation echo. So this is a wall light curve information with EHT observational expected EHT observational time. So this light curve is composed of plenty number of light curve of the gas clouds, and also includes the systematic noise coming from the synthetic data process of Event Horizon Telescope. But if we perform some periodic analysis, we can still obtain the periodicity of radiative echo. So today, I would like to introduce the superposed shot analysis, which is used for the X-ray binary periodicity analysis. So if we first split the light curve into the about 100 RG/C time interval, which is a characteristic time scale of the radiative echo, and then we align each radiation variability with maximum peak component. So we assume the maximum peak as the direct component, and reduce the random property as the direct component. and then we sum all aligned radiation property and obtain the superposed light curve information. So right panel shows the result figure for superposing all time being information, and we can successfully obtain the secondary peak component and uniquely determines the black hole spin value. So this is only for the spin equals 0.9 case, but we also confirm the similar property at the spin equals 0 to 0.98. So this is based on the, quite simple gas cloud model without, because the structure of the gas cloud does not change during the observational time. So finally, we introduced the time variability of the gas cloud by using the three-dimensional GRMHD simulation. So this is coming from the IHAM 3D GRMHD simulation model from Illinois group. And we can see the snapshot image of the around the black hole as shown in the left panel. So this model is based on MAT spin equals 0.94 case, but we also check the non-spin case and check the similar properties. And the middle shows a total light curve of total flux direct component and secondary component. As you can compare the black and the blue curves, the most of the radiation component coming from the direct component and outside from the ISCO. So, but in order to extract the black hole spin information from this light curve, we need to mitigate the direct component from the total light curve information. So we simply perform the linear fitting and extract the residual of the light curve information, like left panel. So left panel shows we again focus on the characteristic time scale of the radiative echo and fit the linear fitting and take residuals. So right panel shows the residual light curve information, and we can see the short time scale variability for the coming from the secondary component and other systematic noise component. So this right panel includes the secondary and other noise component, but we can extract the secondary component by using the superposed shot analysis introduced in the previous slide. So this is the result of the superposed shot analysis, and left panel is the total flux light curve, and the right panel is the direct and secondary component light curve. So if we focus on the right panel, the combination direct and second peak provides two characteristic peak around 0 and 20 RGO. And importantly, the time interval between each peak is consistent with the previous simplified gas cloud models. So what we found is even if we change the black hole spin value, inclination angle, and the characteristic case of the gas cloud model, the radiative echo can be detected in the short time scale. My screen stopped. Wait. So latest IHT development is related to the time variability accelerate our methodology. So this is the synthetic.
Excuse me, we don't see your talk anymore.
Oh no.
Yeah.
Can you hear me?
Yeah, we can hear you, but we just don't see your talk anymore.
Oh, okay. Yeah. So this is the final slide. Sorry. Yeah, that's for.
Oh, okay.
Yeah.
Okay, because we don't see it, but maybe. Okay. I don't know, with the problem with the sharing, maybe.
Can you see my screen?
No, we just see you there.
Oh, I see. Sorry. Is it now?
No.
So
okay, now it came back. Super.
Yeah. So did you see this slide before?
Yeah, we saw this one.
Okay.
It was
Okay.
when you
Sorry
put...
for that. Yeah. So this is the EHT latest time variable extraction challenge accelerate our method for black hole spin values. So this is synthetic data reconstruction for the short time scale variability from the near future EHT observational coverage. So left panel shows the ground truth hotspot rotation movie. And if we perform the synthetic observation of this short time scale hotspot movie with a period of 30 minutes, we can still obtain the position angle mode for this kind of hotspot motion. This development was our process can be accelerated due to the latest improvement of the EHT observation and corresponding methodology. So that's all. The summary is we obtained the independent method of the black hole spin measurement compared with the previous effort and shows the detectability of the radiative echo with the 2017 and 2022 EHT UV coverage. And the next step, we would like to move on to the direct comparison between GRMHD synthetic observation and real observations. That's all. Thanks so much.
Thank you very much for your interesting talk. Do we have questions? We have 5 minutes. So please raise your hand. Okay, we have one. Wow, Paulo Brito, your question?
Yes, yeah, okay, thank you for this presentation. And I would like to know if there is some way to measure the charge of the hole with using these echoes.
Charge. This is does not include the charge parameter of the black hole spacetime, because the astrophysical case, the charge will be neutralized with surrounded ionized gas cloud inclusion. So yeah, thank you so much. But yeah, so for the only for the black hole spin case, we focus on the only temporal variations, such as only light curve information. But if we combine the information of the spatial information and the temporal information, we may obtain the deviation from the of the curve black hole, like charge and other extra general relativistic effect.
Okay, thank you.
Okay, thank you again for your talk. Maybe if there is no other question, so we can go to the next talk, next speaker. So it will be Patrick Mack, who will talk about accretion of the relativistic velocity of gas onto a moving charged black hole. Please.
Hey, thank you very much. Okay, can you see this slide?
Yeah.
Okay, perfect. Thank you very much. So the work is done together with Andrzej Odżywałek, and if you are interested in any details, then this is published in those 2 papers. Now, this will be, I guess, a huge change in the character of the talks, because what I would like to present right now is an purely theoretical work. It's an analytic solution that corresponds to a Schwarzschild black hole moving through a cloud of gas. And it's basically understood to be a general relativistic analog of what is sometimes called the Bondi-Hoyle-Littleton problem. Now, our approach is to find an exact solution to the Vlasov equations describing such system. What we assume about the gas is that it's thermalized at infinity. That is, it obeys the Maxwell-Eutner distribution there. And apart from that, we understand that the gas is collisionless. This is, of course, an approximation, but well, this allows for the calculation. And hence, in the vicinity of the black hole, the gas does not have to be in thermal equilibrium any longer. And in fact, if you compute, say, the pressures, you will see that the pressure, for instance, is no longer isotropic. Now, apart from that, the description is very standard to those kind of models. We describe the system from the point of view of the black hole. So we work in standard Schwarzschild spacetime, and we just assume that the gas is moving uniformly at infinity with a given speed, right? So, of course, in order to do this, we have to boost the Maxwell-Eutner distribution appropriately. Now, what is known about such systems, or rather, what is the literature on this problem? Well, of course, there are those classic old papers starting from works of Hoyle, Littleton, and Bondi in 40s. And these are, of course, Newtonian papers, very clever, slightly hand-waved, mostly in what we would nowadays refer to as a ballistic approximation, I guess. And then there is a kind of solution by this Russian group in '79. Now, when it comes to general relativistic solutions, there is a very famous solution for perfect fluids. It was published by Petrich, Shapiro, and Tucholsky in '88. But the trouble is that it works for ultra hard equation of state. That is when the pressure is directly equal to the energy density. But the bonus is that you get a solution both for Schwarzschild and immediately also for Kerr metrics. Now, of course, there are relativistic hydrodynamical simulations. And I was trying to, well, collect basically most of the authors here. I think starting from Papadopoulos and Font. But I also would like to mention a recent paper by Tejeda and his student, I guess, where there is a relativistic solution in the ballistic approximation. So that is, the gas is not in thermal equilibrium at infinity, but at infinity you simply assume that all the particles travel in a direction parallel to the motion of the black hole. But I have to mention a crucial paper for this work, and this is the exact treatment of the Bondi type that is spherically symmetric accretion on the Schwarzschild black hole. And this, of course, refers to a non-moving black hole. And this was done by Paola Rioseco and Olivier Sarbach in 2017. Now, it's crucial because this is where they develop the formalism that, as it turns out, can be used right now for moving black holes. So just to briefly introduce that, we work in Schwarzschild metric. Since we are talking about accretion, we work in horizon penetrating coordinates. This can be done quite generally, but just to focus attention, let me choose such coordinates. And the formalism is based on a Hamiltonian approach. So this is also well known that a particle, a geodesic particle, can be described by a Hamiltonian, which can be simply taken in this form. And here, this pair is understood as canonical variables. So if you write the Hamilton's equations for this Hamiltonian, you get the geodesic equation. Now we require that this Hamiltonian is normalized so that this is, well, -1/2 m squared, where m is the rest mass of the particle. And by standard arguments, there are constants of motion, of course, here. The energy, the Hamiltonian itself, the azimuthal angular momentum, the total angular. Now, in this formalism, you get Vlasov equation very easily simply by requiring that the distribution function that describes the gas in the phase space is conserved along a geodesic. And if you write down this requirement, you get a Vlasov equation in the form of this equation, where you recognize the Poisson bracket at the left-hand side. Now, interesting physical variables can be obtained by integrating over momenta. So, for instance, the particle current density J mu can be obtained by such an integration. And by Vlasov equation, it's conserved. Moreover, you can define covariantly the particle density simply by taking the square root of the square of J mu. Now, it turns out that the Vlasov equation in this form can be solved formally by a canonical transformation to new coordinates, denoted here with those uppercase letters. And this is done in a fashion basically borrowing from Hamilton-Jacobi approach. You define the abbreviated action by this integral along a geodesic. And by new momenta, you take the constants of motion, and as the conjugate variables, you take appropriate derivatives of the abbreviated action. It turns out that for this calculation, we only require Q3, which can be computed. And this is a canonical transformation. So basically, the Vlasov equation, which is given by a Poisson bracket, is covariant with respect to canonical transformation. And because Hamiltonian is essentially one of those momenta, then the Vlasov equation reduces to this derivative of f with respect to one of the variables. So basically, any function f that is independent of one of those variables, Q0 here, satisfies the Vlasov equation. Now, of course, we do not need to have any solution. What we need to have is a solution which is axially symmetric and stationary in our case. Now, this is a little bit more complex how to do this, how to impose those conditions. You basically have to lift the Killing vectors to the cotangent space here, but essentially, you end up with a result that such a solution should also satisfy those conditions. So in particular, if you take any function that is independent of Q1 and Q2, this would do the job. So in what follows, we search for solutions in that form. Now, of course, this would be a sort solution of the Vlasov equation, but we have to specify it right now. And we specify it by implying the boundary conditions. And those, as I mentioned already, should correspond to a boosted Maxwell-Hüttner distribution, which we can start computing in the Minkowski spacetime. So for instance, since I would be working in spherical coordinates, we take Minkowski spacetime in that form. And if you think about the boosted Maxwell-Hüttner distribution for a monoatomic gas of same mass particles, then it's given by such an expression where, of course, this delta ensures that these are same mass particles, but the function f is given precisely by this expression. So when v is 0, then this reduces to the standard Maxwell-Hüttner exponential form. Here, gamma, and this will be playing an important role, is the Lorentz factor associated with the velocity of the black hole, that is, in our description, the asymptotic velocity of the gas, and beta is basically the inverse of the temperature. Now, it turns out that you can express this formula for the Maxwell-Hüttner distribution by our new coordinates. And after a sort of lengthy calculation, you get this formula. Here, epsilon basically correspond to the directions of motion along the geodesic, but apart from that, all new variables are precisely analogs of what I have just introduced for the Schwarzschild spacetime. So it turns out that by construction, this is a solution already, right? Of course, it's written in unpleasant coordinates, but by construction, this treated as a global solution in the entire Schwarzschild spacetime is a solution to the problem. Now, of course, physically, we would be interested in something different. Namely, we would like to know how to compute interesting variables. For instance, how to get the, say, the density, the particle density, or the particle density current, or, well, pressures, if you would like to, and so on. Now, this is slightly more complicated. And I regret that I had to introduce a little bit of notation here. So it turns out that it is convenient to work in dimensionless quantities. So xi basically is a dimensionless radius, p's are dimensionless momenta, and epsilon is a dimensionless energy, and lambdas are dimensionless angular momentum. Now, it's also very well known that the momenta, the radial and this theta momentum can be expressed using those formulae. These are absolutely standard for Schwarzschild geodesics. Here, one introduces the radial effective potential, which also plays a role. And for instance, for this quantity Q3, one can obtain the following expression, where x is just this integral, which actually can be even evaluated using elliptic functions, although this is quite unpleasant. Now, the art next is to find coordinates, the momentum coordinates, where or in which you could easily describe the ranges in or the regions in the momentum space occupied by the trajectories that we're interested in. And it turns out that this collection would do the job. So here, basically, I only introduce chi by those formulae, and you can write down the transformed integration element, and moreover, you can also write down the probability function in terms of those new coordinates. So these are those equations here, which quite notably, I think they even become simpler than in this original version. So right now, it turns out that there are two types of trajectories relevant to the problem. So all trajectories relevant to the problem start at the infinity, but if they have sufficiently small angular momentum that they simply get absorbed by the black hole, and if they have sufficiently large angular momentum, that they get scattered by the black hole again to the infinity. And it turns out that you can describe them by some functions that can be derived from the effective potential. So for instance, this is the maximum allowed angular momentum for the absorbed trajectories. And now everything that you want to compute, you compute by splitting into a part corresponding to absorbed trajectories and scattered trajectories. So this is a probably finite lengthy formula. If you do the calculation to the end, this is the, well, analytic expression or exact expression for the particle density current as a solution. Well, basically everywhere in the Schwarzschild spacetime. It's, as you see, given up to 2 integrals or double integrals that you have to do numerically, but you can even work with them in Mathematica. So how does this look like? Well, if you look at absorbed trajectories only, then this is this first column. Then the flow is mostly radial. If you looked at scattered trajectories, that non-surprisingly, this uniform flow is described by in these terms. What you could notice here is, for instance, that there is no scattered trajectory beneath the photon sphere, as it should be. And of course, you can combine everything to see this picture as it emerges from this analysis. And you can also then draw, for instance, the particle density plots. The particle density is color-coded here, so this corresponds to relatively small velocities, and these are larger velocities. What you can observe here is, which is also standard for hydrodynamical models, is the stagnation point beneath the black hole here. And the arrows show again the directions of the average flow here. Now there is an important. I have to hurry up, so let me just be very brief right now. There is an important quantity that you can derive from that, namely the mass accretion rate. After a little bit lengthier calculation, you get this formula for the mass accretion rate. It's exact, but of course, probably not very much illuminative. So what you can do is, apart from plotting that, of course, you can have limiting expressions. So for infinite temperature limit, what we recover from that is that mass accretion rate is essentially proportional to the Lorentz factor associated with the black hole motion. And this is qualitatively the same result as for ultra-stiff fluids in the solution of Shapiro, Tucholsky, and Petrich. Now, in the opposite limit for 0 temperature, you can get this this expression apart from zero velocity, where the accretion rate is infinite, and where you can have that asymptotic behavior. Now, the characteristic thing about this is that this later case corresponds to the situation where the accretion rate is not monotonic with the velocity of the black hole. So initially it drops down. It acquires a minimum somewhere around half of the speed of light, and then it goes again roughly proportional to gamma again. But for infinite temperature, you've got this proportionality to gamma, which is well, very clearly seen here. Those curves tend to coincide. Okay. So just to summarize those results, well, the bonus, of course, is that this is the exact solution, and the final the final expressions are relatively compact. Now, those accretion rates basically interpolate between those two regimes, with the infinite asymptotic temperature and the 0 temperature case, which, by the way, could be obtained from the ballistic approximation, for instance, that one by Tejeda. So basically, we are in between of regimes that were already known in the literature. Now, when it comes to applications, I would say that I would imagine that this could have or find some use in the situation when you do not necessarily believe that your matter around the black hole is in thermal equilibrium, so basically then the hydrodynamics no longer hold. But another very natural application would be at the context of dark matter. And now it seems that nowadays the accretion rate would be well, probably insignificant for a larger growth of black holes. But for instance, if you do an analysis in the spirit of well, Zeldovich and Novikov, this is a very old paper from '67, and consider the accretion in early epochs of the universe, then this could it can be shown by a very hand-waving analysis that this could play a role. Okay, so thank you very much. Okay.
Audrey, you are muted.
Okay, I don't hear you, you know.
Oh, sorry, I was muted.
Okay.
Sorry. Thank you for your interesting talk. Just maybe one question really quick. Yes, Professor Kaas?
Just a quick question. Given your solution, you could probably calculate also the dragging force, which slows down the motion of the black hole by its gravitational interaction with the medium. In analogy with the classical von de Hoyle-Littleton Newtonian.
Yes.
So did you try to do it?
No, I didn't. No, I didn't. I didn't do this yet, but thank you very much for the remark. Of course, this should be done.
Well, the main question was whether you have at least anticipation if it comes out infinite or finite.
Can be treated, electrons can be treated as in the force-free approximation, while protons, ions, heavy ions, or even dust have to be treated in the non-conducting approximation. Okay, so I would like to start with motivation for study of dielectric or non-conductive toroidal structures. We were studying motion of charged particles around Kerr black holes, and we have found, for example, in the case of uniform magnetic field, the Wald solution, or even for dielectric or parabolic split monopole case, we have found possible existence of off-equatorial circular orbits. Then it is quite nature to treat the situation when there is a lot of charged particles and some toroidal structure can be rotating around a black hole. It can be stressed that the toroidal structures can be separated above and below the equatorial plane, or there can be crossing the equatorial plane. It depends on the conditions. So, having such structures, we have a variety of possibilities how to treat these configurations, charge configurations. The basic situation is cloud of non-interacting particles. The more involved situation is related to kinetic theory, when we can consider, say, collisionless plasma. And the most sophisticated case is gases and liquid fluid plasma with high densities. In all the cases, we observed fluid levitation. That means that the toroidal structures can levitate above the equatorial plane. Of course, I would like to stress that the toroidal structures can parallelly exist also in the equatorial plane. It is not excluded. Dynamics in this case is given by gravitation, electromagnetism, and in such structures, pressure is very important. So we are using standard pressure equations, integral form, when we have some potential, effective potential which governs the behavior. It is standard approach developed, for example, by a group of Marek Abramov. This theory is related to equatorial structures which are centered around equatorial plane, and this can solve very well some basic observations related to accretion disks in active galactic nuclei or in microquasars. Well, when the electromagnetic interaction is put into the game, we can consider the energy conservation, Maxwell equations, flow of electricity, and then we can consider tensor of matter, tensor of electromagnetic field, and electromagnetic field external and internal. The point is that in our model, we consider that the internal electromagnetic field generally is much lower than the external magnetic field. And as I said before, we have the opposite of the force-free approximation. So we are putting sigma conductivity equal 0, and the electricity is connected, or electromagnetic field is connected with the motion of particles. That means in this case, we are not able to forget about rest mass of the particles. So the basic equation for behavior of such structures is relation in between the balance of matter, stress energy of matter, and with balance of the electromagnetic forces caused by the external magnetic field. Well, in having solution of such cases, we have charged Euler equations when this can be separated and can be solved with integrability condition satisfied. And in this case of non-conducting structures, we can make charge transformation, and the electromagnetic potential can enter the potential, effective potential governing behavior of the structures. So in this case, we can obtain two interesting cases. One case is the levitating toroidal structure, which is slender, can be slender torus. And the other case is the polar cloud. And we are able to show that in both cases, the polar cloud or the slender torus can be located in the region where generally the jet created by the Blandford-Snarek process is located. So it means that in these special circumstances, there can be obstacle for the jet. So this is the first point. The second point is related to Keplerian disks ionized near the ISCO. And this is important that we can assume that the ionization can be realized, for example, by decay of neutron, or it can be caused by irradiation and escaping of electron from hydrogen or heavy particle. So what is relevant here is the case that we are considering electromagnetic fields which are realistic. For solar mass, it is going to 10 to 8 Gauss. For the supermassive black holes to 10 to 4 or even 10 to 5. Now, what is important is ratio of the gravitational and electromagnetic forces, and this is very important. So, in this case, we have several very important consequences. The one consequence is related to the shift of innermost stable circular orbit because of the electromagnetic interaction and possible existence of off-equatorial orbits. Second case is charge particle oscillations and modifications due to this process, then the magnetic Penrose process, and finally the radiative Penrose process. So, in the case we are considering, the electromagnetic force can be in some circumstances much, much higher than the gravity, and this can be very efficient in obtaining the acceleration of particles. It is quite enough to consider Lorentz equation to follow behavior of the particles. And I would like to give one interesting special case when the originally regular circular motion in Keplerian disk of neutral matter is changed into the period of chaotic scattering. This chaotic scattering is resulting in, again, regular motion along the magnetic field lines. So, the Penrose process can be characterized by the energy conservation and charge conservation. So, we can obtain the case I described when the particle is accelerated in the very neighborhood of the black hole and escaping with very high velocity and energy along the magnetic field lines. Well, so we can demonstrate that the Penrose process can have three regimes which describe efficiency of this Penrose process. The original process for uncharged particles is of very low efficiency, lower than 0.21. Maybe it could be stressed that this is the case of Kerr black holes, but we can show that for Kerr naked singularities, this efficiency could be slightly higher, but not by order, only slightly. Then there is moderate case related to the charged matter when the efficiency is going up to, say, 10, as in the Blandford-Znayak process. And finally, the version of ultra acceleration, which can be as high as 1 billion or even higher, this efficiency of acceleration. And the point is that in this case, we are using neutral matter to reach the regions where the strong efficiency of the acceleration is possible, and then the acceleration can be really so high. So this is the possibility of existence of ultra-high energy, and we can demonstrate energy of the proton, for example, which can be given as 10 to 20 electron volts for proton and magnetic field 10 to 4 Gauss and black hole of mass 10 to 9. Of course, now we observe masses and magnetic fields by 1 order higher. So, as I mentioned in the beginning, the energy 10 to 22 electron volts can be obtained in this way in very, very simple process. Well, so considering the quasi-periodic oscillations, we are able to demonstrate that the oscillations related to some hotspot can be very well fitted to the observations, even in the case of supermassive black holes in active galactic nuclei, where several months ago, Robert Wagoner and his colleagues demonstrated that for standard geodesic models, it can be almost unable to explain such frequencies. So we are able to demonstrate that this is possible. And I would like to stress that we are considering motion of the hotspot, but to be correct, observations demonstrate that the hotspots are probably more similar to very slender tori or something like that. So for this reason, we are using not the relativistic precision model, but the epicyclic frequency model, where the upper frequency is related to the latitudinal oscillations usual, and the lower frequency is related to the radial oscillations of such toras. Now, you can see how the electromagnetic interaction can influence position of the ISCO, and it is clear that this is dependent on the character of the magnetic field, and in any case, for the positive electromagnetic interaction, positive parameter B, the decreasing of the ISCO is clear. Well, so what is relevant for our model is the case of the motion of, say, hotspot or oscillatory motion of slender toras, which is related to the very close neighborhood of the horizon of the black hole. And what is interesting is the crossing between the radial epicyclic frequency radial profile and the vertical frequency radial profile. This crossing is crucial for our explanation of these processes. Well, so when we observe the data which are obtained for microquasars, quasars, and together quasars and microquasars, we would like to stress that the crucial point is related to the fact that there is the ratio not only 3:2, but also 2:3 between the vertical and radial frequency, and the existence of 2:3 ratio is the crucial point for possibility to explain the data in the case of supermassive black holes. Of course, the data can be well explained for microquasars in the standard way. There is almost no strong influence necessary. So finally, I would like to mention the final new radiative Penrose process, which will be recently discovered, and this is related to the motion of charged particle in magnetic field with the back reaction force taken into account. I would like to stress that in dealing with this back reaction, we are using two facts. First, that the tail integral of the back reaction can be abandoned in this case. Second, we have a Ricci flat solution. So there is only the term which contains the third derivation of position, but it is very difficult to be solved. So we are using so-called Landau-Lifshitz trick, and this is able then to use it and demonstrate how it behaves. So, orbit of particle without radiation is conserving energy, and the particle is moving with no troubles. Under standard conditions, when, for example, the particle is moving in the, is co-rotating with locally non-rotating frames, then the solution of these equations is standard and very simple, and the energy of such particle is decreasing because of radiating energy by the synchrotron radiation is positive. So this is standard situation, and such a particle is falling down into the black hole. But we can obtain very unusual case, and this is the new version of the Penrose process. We call this radiative Penrose process, when inside of the ergosphere and only there, the energy is increasing, and after crossing the ergosphere, the energy of the radiating particle is decreasing. So this is very interesting phenomenon, which we assume to have very important consequences in modeling the processes in very close vicinity of the black hole horizon. In any case, it's very relevant even for one particle motion or test particle motion, and it is clearly demonstrated in this case, but we assume that even on the level of collisionless plasma, this can be treated, and we are doing first calculations on this way, and it can be very relevant also from the collective point of view. The last interesting point of this case is related to the situation when we are obtaining special trajectory which is oscillating or floating around energy boundary, which is taking energy while being above and losing energy being under the horizon, being inside the ergosphere and being outside, it is losing energy. So this is oscillatory motion, and if well tuned, the parameters enable to have long-term motion of this kind. Well, maybe the last point in this way is to give the basic explanation of the radiative process. And this is the explanation is very simple. The process is related solely to the ergosphere of the black hole, having nothing to do with effective ergosphere. And it is caused by the radiation of photons having negative energy as related to distant observers. Such energy can be obtained in any case, but it will be amplified if the radiating particle is counter-rotating relative to locally non-rotating frames, and the beaming effect amplifies the negatively valued photons and the total negative energy of radiated photons overcomes those of the positive energy. And of course, then the covariant energy of the radiating particle increases. So this is very simple explanation. We are preparing more detailed paper on this case. And of course, we are planning to continue investigations of the behavior of radiative Penrose process in various magnetic fields, treating its efficiency and of course its influence in the collective phenomena. So thank you for your attention. I believe I am almost exact.
Thank you very much, Professor Stuttlik. So is there any question? To do that, if you don't know, you can click on reaction and you can raise your hand. Okay, Eva, please.
Yeah, hello. Thank you for this very nice talk. I have a question about this type of magnetic fields that enable the off-equatorial circular motion. I know that this is possible for the Kerr-Newman if you take into account the magnetic monopole charge. Is this like a general feature of, say, any magnetic field, or do you need some special, say, fine-tuning?
In fact, any magnetic field, poloidal, with poloidal components, enables this.
Ah, okay. So, and is this also always stable? Can one say something about that? Say, not only radially, but also in the, say, theta direction?
Of course, surely these are unstable because of the radiative reaction. This is clear. Generally, I expect that mostly in this case, they can be stable, but I'm afraid that in the case of equilibrium on the axis, this unstable case is more probable. According to my knowledge in Kerr-Newman, it is impossible to have stable position on axis, but I am not excluding that some magnetic field could enable this, but probably not.
Okay, thank you very much.
I don't know about the case when it will be stable on axis.
Okay, thank you.
We have a question which has been written in the chat. I don't know, can you see it, Professor Stuttlik? Or maybe I can tell it.
Mm-hmm.
Do you see the question?
Considering the radiative flow, it is clear that its influence is much lower. It is non-zero influence, of course, but it is much lower.
Okay, is there other question? Okay, if not, I would like to thank you again, Professor Stuttlik, for your really interesting talk.
Thank you very much.
Thank you. And we can go to the next speaker. So Professor Stephen Berbis, which is going to discuss about time-dependent Kerr disks and tidal disruption events. So please, Professor Berbis.
Okay, fine. Can you hear me, Audrey? Am I on?
Yeah, perfectly.
Okay, very good. So I'm going to talk today about, as you see, time-dependent accretion disks around Kerr black holes and the relation to observed tidal disruption events. And I'm going to make sure that I put my graduate student, Andrew Mummery, front and center, because he's done both of course, as usual, almost all of the work, and many of the ideas that I'll talk about are today in the talk originated in discussions with him as well.
You're welcome.
I'm sorry, was that okay?
Yeah,
No,
I think just someone was unmuted, but I did it.
okay. So modern accretion disk theory, of course, began as a search for evidence for black holes at a time when black holes were still considered to be controversial. And the seminal paper was written in 1973 by Rashid Sunyaev, one of the most cited theoretical papers of all time. It had, I don't know, 4,000 or 5,000 citations the last time I looked. And it became this sort of canonical.
Excuse me, I cannot see your slides. I don't know if anybody can.
Oh,
Me neither.
that's because you're right. I'm sorry. Let me go back. You should have said something earlier. How are we now?
No, we don't see
Nope.
it.
How
I thought
are
it
we
was.
now?
Oh yeah, perfect. I thought it was your
All right.
introduction. Okay, good.
I apologize for that. Let me quickly scoot back. So this was the first slide, the second slide, third slide. Haven't missed anything terribly crucial as of now. So the theory, of course, that I will be discussing is the theory of thin disks, and that's defined by the condition that the rotational velocity, r omega in standard units, omega is the angular velocity, v rot is the rotational velocity, is much larger than the thermal velocity for a thin disk, which is essentially saying that the disk height h is much less than the radial location r. So in the radial direction, there's rotational support. In the vertical direction, there's pressure support. So after the seminal Shikura and Sunyaev paper in 1973, accretion disk theory developed rather rapidly. The time-dependent theory in the Newtonian limit was produced in 1974 in another classic paper by Linden, Bell, and Pringle. And in pretty short order, the relativistic theory for accretion disks appeared due to the work of Novikov and Thorne, and then in more detail, Page and Thorne. But for some reason, there wasn't very much development. In fact, when I researched into it, there was hardly any development at all in terms of the relativistic time-dependent theory. And was a bit surprising. People sort of worked with steady state models almost exclusively in the relativistic domain, and not so much time-dependent models, despite the fact that they would be quite useful in terms of understanding observations. So in 2017, I went through and did the derivation for the relativistic time-dependent theory, and thought that was somewhat to my surprise the first time that it appeared. But no, one of my colleagues pointed out that in a paper by Eardley and Lightman, in fact, in 1975, in the appendix, without any note of explanation, the form of the relativistic thin disk theory appeared, and it just sort of stayed there for about 40 years before somebody did something with it. So what I'm going to talk about today is, in principle, something that could have been done in 1975, but for some reason it just kind of lay fallow there for many years. And it is, I guess, the stimulus of these tidal disruption events, which has sort of put this kind of theory into play now. So let's talk about the disk evolution equations. I'm going to go through a bit of the maths. So we work in standard cylindrical coordinates. And the disk is turbulent, so it is going to consist of a mean flow, as you see, V phi has a rotational R omega component plus a delta V phi. The radial drift from the accretion itself consists of a fluctuating component, the delta VR, and then actually a very small inward drift due to the dissipation. And of course, that is the accretion process itself. The relative asymptotic ordering of these variables is that the rotation velocity, R omega, is much bigger than a typical RMS fluctuation. And that in turn is actually very large compared to the radial drift velocity. So we have three distinct scales. And the quantity of interest, what people kind of informally refer to as the disk viscosity, it's not something I favor. It's not a name I like any more than convection is thermal conduction, because this correlation VR V phi in a turbulent fluid can behave in much more subtle ways than a viscosity. But in any event, it is, we plug in from the expressions above for the mean flow plus the fluctuating flow, we find this VR V phi, which physically represents a sort of angular momentum transport, is due to a direct transport of R omega, what Donald Lindenbell liked to call Laurie transport, plus the WR phi, which is due to the correlated fluctuations. Note that they have to be correlated, not just present, and they have to be correlated in a positive way. And in general, that will happen when you have a weak magnetic field present. It's been shown that the MRI, something I worked on 30 years ago, in fact correlates the velocity fluctuations in just the right way so that it does act in this sense like a viscosity. The fundamental equations, if we go back now to Newtonian theory, are very simple. There's mass conservation and there is angular momentum conservation. And of course, I have height integrated here. And these take on the simple kind of generic form of a d by dt of some kind of a density plus a divergence vanishing. And the solution for the disk equation can be obtained very simply by solving the angular momentum. Looks like V is kind of buried in there, but in fact, it's possible to solve this equation directly for V and then plug it back into the mass conservation equation. And then what you wind up with is a very nice looking diffusion equation. This is the standard thin disk, what everybody likes to call the viscous disk evolution equation, first derived by Lindenbell and Pringle in 1974. And you notice that it has kind of in this form of something like a diffusion coefficient, there is a gradient. That prime there is a d by dr. So the angular momentum gradient comes in. I'll speak a little bit more about that in a moment. WR phi contains the correlated velocity fluctuations that I just spoke about. And I've slipped in something that's not part of the view graphs, but can be part of the analysis. When you have a magnetic field, what comes in is the correlation of the Alfvén velocity components, in addition to the fluctuating velocities, kinematic velocities. And in fact, it is the Alfvén components, the Maxwell stress in the WR phi, that dominates, we believe, in actual astrophysical disks. Finally, this gives me an equation. Once I know what WR phi is, that's where you have to sort of be creative and decide how the correlated fluctuations are going to behave. But once I know that, I can solve that for the density. And then to actually calculate the emissivity, I use a standard result from fluid theory. And I've written it in the form here as so-called stress by strain relationship, the TIJ. It's basically the same thing as what I've called WR phi, except it's proportional to a density as well. That's the stress tensor associated with the fluctuations. And then the DJVI here is the strain, stress by strain. And that's the rate at which energy is extracted from the large scale shear, goes into fluctuations. And in standard disk theory, the idea is that once The energy is in the fluctuations. It gets thermalized and emitted like a local black body, which is how we figure out what the disk spectrum should look like. And then the other point worth mentioning that we take over from Newtonian theory is that, of course, r squared omega, that's the specific angular momentum, and that gradient in Keplerian flow is positive. And that means that, of course, the flow is stable by the Rayleigh criterion, not a surprise. And that means that our mathematics is well behaved and that this really does act like a diffusion equation instead of behaving unstably as you would have if you had a negative angular momentum gradient. And of course, general relativity is interesting because what I just said is not true everywhere in an accretion disk. There is an innermost stable circular orbit, an ISCO, where the gradient of what is the proxy for angular momentum, when effectively the angular momentum gradient vanishes. And of course, that's a very salient and critical point in the analysis, and it requires sort of careful work in the vicinity of the ISCO to solve this equation. And the Lynden-Bell-Pringle equation has nice, in some cases, when you make simple assumptions for the form of the stress tensor or the viscosity, that can be solved analytically, and you get the classic feature of disk spreading as shown in this nice example from Pringle's 81 review paper. Moving on to the relativity, we have a similar type of calculation. Of course, we do this now in a more complicated geometry. So I've written down for you here the line element. We're going to work in the Kerr midplane, and that means theta is pi over 2. In the equations, the speed of light has been set equal to 1. The angular momentum parameter A is j over m in these units. A, think of it as having units of length. It's of order, the gravitational radius, rg or gm. And I've written rs as 2gm here as a shorthand for the Schwarzschild radius when it appears in the Kerr metric. So this will be, I'm sure, pretty familiar to most of the people in the audience. And my notation here is that capital U mu is a 4-velocity, derivatives always with respect to the coordinates, and the covariant form is calculated in the usual way. The fundamental equations, the analogs of the Newtonian case, are the, put those up, the conservation of particle current. The semicolon, of course, in the usual way, represents the covariant derivative. So this is a covariant divergence vanishing. The stress tensor, relativistic stress tensor, takes on the standard form for an ideal fluid, except that we actually need to add the radiation here, because once we're in the vicinity of, or once the length scale is of order the gravitational radius, the angular momentum carried off by the photons is not negligible. That needs to be included in the analysis. And then the angular momentum equation is just the divergence of this T mu phi vanishes. And of course, that is a less complicated equation than it would be in general because of the symmetry. D by d phi is a killing vector for this problem. Just to remind you of the idealizations, because I'm going to be not just doing the theoretical calculation, I'm going to be actually applying this to observations. So we need to understand what mathematical idealizations have gone into this. The assumption, of course, is the disk is thin, in this sense cool. Pressure is ignored compared with rotation, at least in the radial support. The velocity field consists of a mean plus fluctuations, and the r phi components, now these are relativistic for velocities, are correlated. I put a little star here. Oops, note that the w r phi, I have to be careful now where I am putting my indices, of course, in the relativistic calculation. The phi is a covariant index, and that means w r phi is truly an angular momentum correlation now, not so much. So this u phi here is not a velocity; it's actually an angular momentum variable. And right, the u phi refers to the mean flow, and the equations are height integrated over the small dimension h. When we put everything together, we wind up with, of course, in relativity, all the equations get longer, and this is the form of the evolving equation. And you see this extra kind of ugly looking piece, or it looks like it's ugly. It's actually going to get simple in a moment. That is the angular momentum carried off in radiation. When we write down the stress by strain relationship in relativity to actually see what the disk looks like, we need to do that, of course, more carefully. And the analog of the Newtonian equation, the stress by strain equation that you see in the bottom, in relativity looks very much the same. There's a u phi over u0, the only difference being essentially the clock that is involved, whether it's a co-moving clock or the clock that's observed by the clock according to a distant observer. That's what the u0 here measures. But in principle, the calculation is exactly the same type of thing. And then, of course, if you do it carefully, you have to do ray tracing and keep track of the photon orbits when they're coming from the disk near the scale of the gravitational radius. So using this equation, replacing Fz by this quantity, the du phi times over u0, in fact, the equation starts to look a little bit more presentable. I've defined this auxiliary variable y absorbing g. I didn't say g is the determinant of the metric, which is pretty simple for the curve midplane. The square root of g is r squared in spherical coordinates, and if I'm using the cylindrical coordinate, it is just r. And right, the u phi over u0, that defines what I mean by omega here in this problem. So the interesting thing here is this u prime phi, that is the angular momentum variable that vanishes at the ISCO at 6rg for a Schwarzschild disk. And it is a singular denominator. And in fact, when you work with this equation, that requires some care. Here are the angular momentum. In black is the Newtonian r squared omega profile. And the purple here is the Schwarzschild u phi. And you see that it turns up at the ISCO location 6rg. And one of the interesting things, or one of the interesting questions in disk theory, is what we should do with the boundary condition for the stress at the ISCO. Do we set that equal to 0, as it would be if we're thinking in terms of a viscosity? Or if we have a magnetic field present, is it better to keep a finite stress present? And depending upon which of those assumptions you make, you can get two different solutions to the equation, which in principle are testable through observation. We can simplify this evolutionary equation with yet another step further. If we take this combination u phi log omega primed and call it a q primed, just define that as q, and then it turns out there's this kind of neat identity that you can get from the geodesic equation. A technical point, so I'm sorry to bother you with that, but what it does is it collapses the equation down yet another step, so it looks even more Newtonian. So in fact, with zeta now my variable, which is this y variable divided by u0, I get an equation which is very nice to implement on a computer, or believe it or not, even in some cases actually solve it with pencil and paper, just like the good old days. So I write at the bottom here the Newtonian form of the equation for comparison, and you can see that in fact they are quite similar. So our motivation in doing all this is, of course, for studying this equation to understand tidal disruption events. Tidal disruption events are the passage of a star through the disruptive zone of a massive black hole at the center of a galaxy. And kind of it's been around, the idea in one way or the other, spaghettification, as it used to be called, since the early 70s. In its modern form, it's generally traced back to Rees's 1988 paper, who made this very simple argument that when such an event occurs, we would expect a light curve in the form of the bolometric luminosity, assuming it is proportional to dm dt as the material falls back onto the hole. If I write that in the form as a dmde, a derivative or a ratio of mass per unit energy, times a dE dt, the rate at which the energy changes per unit time, in the form of a v d by dr, then if I make the assumption that I have an equipartition of energy between the masses, dmdE is a constant, v is the Keplerian 1 over r to the 1/2 velocity, dE dr goes like r to the minus 2, then the scaling here is r to the minus 5/2, and via Kepler's law, if I translate that to the time domain, that's a t to the minus 5/3, which should be the generic light curve power law. So when tidal disruption events were starting, or candidates, I should say, were starting to be identified, in fact, at first, the observers thought that they were confirming this, and then they looked a little bit more closely. And in fact, I'll quote this from by 2017, it was clear that this wasn't really quite the way these light curves were behaving. The emissions evolve with power law indices that are typically shallower than the canonical minus 5/3, implying that the X-ray TDEs are viscously delayed. So we know what viscously delayed means. There's obviously an accretion disk forming. And then we should ask ourselves the question, if you have an accretion disk, should we be looking for a power law at all? So early work in this direction was done by Knizia, Lee, and Goodman in 1990, who concluded that with kind of a standard alpha disk model, the power law should be not so much 5/3, but minus 19/16. If we take their work, and that's assuming that the stress at the ISCO vanishes, it's actually much, you clog things up and you have a slower decay. For their same model, that 19/16 turns into 11/14. You always get these weird exponents in these kinds of disk models, minus 11/14, which if you force the fit to the observations is a little bit closer to what is observed. So to do the relativistic case, it's possible to do this analytically. I'm going to go through this very quickly because it's not the main thrust of the talk, but it's a point of interest. So I plotted here what U0 actually is for a Schwarzschild black hole, since that's very simple. And it goes from like 1.4 down to 1. And so there's almost no penalty for simply setting it equal to 1 throughout. And then and certainly that's what you should do if you want to get insight into the mathematical content. And then the equation actually becomes identical to the Newtonian case, except that the angular momentum gradient you use either the Schwarzschild or the Kerr metric for. But it's impossible, in fact, to do quite a bit of work with this with rather standard special functions. And Andy and I have a series of papers on that from 2018 and 2019, if you'd like to see that further. So yeah, these simply relate to doing a piecewise solution to the equation where you use the general relativistic form near the ISCO and the Keplerian form at the exterior and then join them up. But let me get to the sort of astrophysical meaty part of this where theory confronts observations. Let's talk about the spectral evolution of broad and narrow band passes from a disk satisfying the evolutionary equation. So here's a cartoon schematic. X, Y, and Z are my disk variables. Theta observed is the angle on the plane of the sky. I have alpha and beta coordinates for kind of my solid angle on the plane of the sky. And symbolically, I can write with a lot of complication kind of hidden, I can write the form of the X-ray light curve flux as a function of time as an integral over the surface of the disk, and then an integral, in this case, the upper and lower limits correspond to the swift bandpass between 0.3 and 10 keV. I won't take the time to go through the other notation. It should be pretty familiar, I think, to most people in the audience. This is simply a superposition of black bodies. And this, in relativity, of course, you have to do things more carefully. That's why things like tildes and the various variables here have complexity hidden in them. But that's basically the mathematical setup. And to understand what we can do next, let's go to Newtonian theory, which is essentially, we can learn what the basic approach is in a very kind of explicit mathematical form. This is the standard, I think, Lynden-Bell was the first person to write down the flux integral. And it's rather complicated because the temperature as a function of position in a thin disk model takes on this sort of classic form. And when we plug it inside the integral, that's not something that we can do analytically very easily. However, for the X-ray observations that are relevant to the Swift satellite, almost all of the energy is coming very near this sharp temperature maximum that I have sort of sketched some representative curves for here. And in that case, because the temperature peaks so sharply and it appears inside an exponential, we can do a steepest descent calculation to actually evaluate this integral analytically, and not just in a formal sense. The results that we get are actually quite relevant to observation. So I've kind of sketched that out very quickly in this slide here. Basically, the exponential appears in the form of this minus h nu over kt, and then 1 over kt we expand in a power series near the temperature maximum. And that means the first non-vanishing term here appears as this r minus r max squared. So I wind up in the usual kind of way with this approach of integrating a Gaussian. And at the end of the result, I get this rather interesting form. So for an accretion disk, at the very high frequency limit, depending upon whether the temperature maximum, as I've assumed here, is a Gaussian form, or if it reaches a maximum at the boundary, which is actually what you would get if you had stress at the ISCO, then the exponent here is 1 over nu rather than 1 over nu to the 1/2. The point is, in either case, you don't get a Wien spectrum at the high frequency end. You get a modified Wien spectrum due to this spreading in the Gaussian or the exponential. In any case, this can now be integrated over the appropriate bandpass, and by taking analytic solutions to the equations, assuming something for the form of the WR phi, you can actually get explicit equations for what you would expect the broadband X-ray flux should be. In other words, what the X-ray light curves should look like. And you get different results for the case of a finite stress or a zero stress at the ISCO. And this value of n, that depends in principle on what you take for the form of the viscosity. But in fact, it's actually rather insensitive. N tends to be a number, no matter what you choose, something of order 0.7, 0.8, 0.9 for the finite ISCO stress. And in this somewhat different formula, something definitely bigger than 1. 1.2, 1.3 for the case of a vanishing ISCO stress. So you don't have a lot of room to play with the n there. So here's an actual fit to the data. To fit the data, of course, we did it numerically, but in fact, the analytic solution works very well. So this is the very well observed tidal disruption event candidate. Assassin 14 Li, and I'm plotting the X-ray light curves. And if you fit a power law, any power law, to the early time decay, you see you start to get into trouble at later times, around 800 days. And an exponential falls off, and the blue is in fact the result from our fit, which has the combination of an exponential times a power law. As you can see, it does a much better job. This slide simply shows the green and the dotted line are the best fit to the data. The numerical model and the analytic model are essentially one on top of one another. And if we want to compare the case of a finite stress versus a vanishing stress, excuse me, so the blue is the vanishing, the best fit for the vanishing, for the finite stress, and the red is the vanishing stress model. So that's, it's not quite so clear. I would say at least just looking at the X-ray data, the finite stress model does a better job at fitting both late times and early times. If we combine the two, we can solve for both the broadband and the X-rays. Here's the best fit. And once we have our disk model, we can then compute the UV fluxes that were observed. This is again 14 Li, and those are very flat. They plateau. And without any further adjustment, each of these goes through the different bands that were observed almost perfectly. So if you get the X-rays, the same model fits the UV extremely well. You may wonder why it is that the UV is almost a flat plateau, whereas the Swift observations show a pretty steep cutoff. And if you look at these are actual detailed calculations of the disk curves at 200 days, 500 days, 1,000 days, 5,000 and 7,000 days. And the shaded region over here corresponds to the X-ray band. You can see between 200 and 1,000 days, you fall off very sharply as the curve moves to the left, and you essentially become exponentially cut off in the X-rays. Whereas this region, which has the very narrow bands in the UV, there is hardly any change at all. The kind of moveward to the left of these curves with times is almost exactly compensated by the fact that the peak is raising them just as the cooling is lowering them. And so for a very extended period of time, there's hardly any change. And then finally, many thousands of days later, you start to drop off. But this is precisely what the observations show. And I think it constitutes very strong evidence that we really are talking about a disk that has formed. There's simply a close-up of what I've just described. By way of illustrating the kind of results that you can get, from the fit, one can deduce a model for the central hole in 14 Li, about 2 × 10⁶. This was consistent with dynamical estimates for the mass of the black hole. In principle, because the location of the ISCO is sensitive to the black hole spin, you can constrain that, although not quite as tightly. There's a little bit more free play. For this particular example, the best fit corresponded to an A of 0.75. The 2 × 10⁶, I think, is pretty solid. This, I think, is less secure. And then the disk model, also not quite as secure as the mass of the black hole, works to about rather small. It's actually 0.02 solar masses. Conclusions. Tidal disruption events are an excellent laboratory to test the dynamics of classical disk theory. The disks are small, they evolve rapidly, and there's a great big black hole that allows for a time scale which is convenient for observers. General relativistic disks violate, of course, the Rayleigh criterion at the innermost stable circular orbit. If you compute the bolometric luminosities for these kinds of models, L goes like T⁻⁻n, then n is less than 1 for a typical finite ISCO stress disk, and is bigger than 1 for a vanishing ISCO stress disk. But in fact, you shouldn't be doing power laws at all when you actually apply it to real observations, because you never really do have a full bolometric luminosity in any one passband. The fits that one obtains, or rather I should say the solutions to the equations can be determined both numerically and in fact analytically. And in fact, they are a useful, if somewhat over idealized, but they're quite, a useful first pass for the observational data, and they actually do quite well. The X-ray curves should have a generic form from the quasi-beam tail, which are a combination of a power law coefficient times an exponential of another power law. And both the X-rays and the flat UV light curves are well described by a disk model. Disk theory is rather happy, as I say, with these sort of detailed observations. And of course, TDEs, I've went fast. Not every single TDE is as nice and lovely and cooperative as 14Li. There are fluctuations, there are state transitions. Many TDEs show jets. So what I'm showing you here is kind of, how shall I put it? It's kind of the hydrogen atom of the theory. It's the very, very sort of basic, vanilla, evolving, relativistic thin disk model that you want to see how it does before you go to more complicated models that you may need for generic cases. And the answer is, I think that a thin disk model, in at least many cases, does rather well, and it didn't have to. There were ways it could have failed, but it didn't. So there is still interesting general relativistic astrophysical fluid dynamics that can be done for old timers with me, like me, with pencil, paper, and a laptop. And that's a nice note to end on. Thank you very much. I'll stop there.
Thank you very much, Professor Berbis. Is there any question?
Yeah.
So, yeah, we can start by Asaf Pierre.
Yeah. Thank you very much for a great talk. I have two questions for you. The first one is, as we know, these tidal disruption events, they have some sort of eccentricity, which can vary quite a lot. So what is the characteristic time scale for the relaxation, to build up of the disk? That is my first question. And my second question is whether you can comment. I saw that in your calculations, you completely neglected the possible contribution of electromagnetic fields, which under certain conditions could be quite substantial.
What do you mean I neglected electromagnetic fields?
Well, in the stress energy tensor that you showed, right, you can have an extra component.
Oh, listen, I've done some work with electromagnetic fields and accretion disks, so I can tell you that we don't neglect them. So what I have done here was to show a very simple model so that one can understand the origins of the turbulent stress tensor. In the beginning of talk, you remember I slipped in the Alfvén velocities. In a magnetic field,
right.
Not only is it important, it really needs to be there if you actually model the stress from first principles. Otherwise, the disk wouldn't be turbulent in the first place. So in reality, the electromagnetic fields are there. If the magnetic field becomes very strong, then the thin disk model itself breaks down and you get all kinds of other events, which is true. I haven't addressed in the talk.
So, so what would be the kind of typical upper limit of magnetic energy density, which you could still say that the thin disk is valid in this case?
Yeah, so good question. So typically, what you're looking at is the magnetic field energy density should be no greater than the thermal energy density. So the limit of the thin disk approximation is that both the thermal velocities and the alphane velocities should be very much less than the rotational velocities. In terms of the thin disk limit, you also want the magnetic field to be small compared to the pressure so that it's not affecting the equilibrium very much. And that certainly doesn't hold in every single kind of disk and doesn't hold in every TDE disk as well. That's why you get things probably associated with state transitions and coronae and much more complicated phenomena that we all know about. I didn't come to your question though about the eccentricity, which is a good one. So in the beginning, of course, as you said, these disks can be highly eccentric. And depending upon what you're looking, if you're looking in the optical, that's a strong consideration. If you're looking at later times at the UV and at the X-rays, then you're talking about very, very close to the hole. And those circularize, I think, pretty quickly.
Pretty quickly, meaning in what?
Couple of 100 days.
Days.
Yeah.
All right. Thank you very much.
Okay. Thank you for your question.
We have a question in the chat. Can you see it?
Why don't you read it to me? Save time.
When compared to steady state models, does inclusion of relativistic time dependence affect the black hole spin measurement carried out through the position of the ISCO?
Yes, that really does need to be a relativistic calculation.
So we have another question from Tushar Mondal.
Yes, so hi Balbus, so very nice talk. I wanted to know when you fitted the data with like ISCO stress condition with that TD light curve. So there is also other degenerate parameter could be that viewing angle of the disk. So what is the motivation of taking face on disk here?
I'm sorry, I didn't quite get what you said. It's a little bit rough. Could you speak it slowly and then ask the question again? I apologize.
Okay, so when you fitted that light curve data with that exponential plus into that power law.
Yes.
So for both the condition like ISCO no stress condition and with some finite stress.
Yes.
So there could be other independent parameter is that viewing angle of the disk. Like
which angle? I'm not getting the angle name. The queuing angle?
Yes. The disk face on disk you consider right here.
Well, right. There is. I'm assuming that the disk is orbiting in the midplane, and there is the viewing angle. Yes, that also had to be fit as well. Yep.
So what is the motivation here of taking only the face on condition? Because that can also change that power law into that exponential part, right?
I don't know what are you saying the Pearson condition? It's not a name I'm familiar with.
No, I'm asking that power law condition. I mean power law, that value index that may change if you change that assumption.
No, the power law doesn't change that much. The overall normalization does.
Okay.
Yeah.
Also that Doppler boosting, I mean shifting also taking care when you consider that.
Oh yes, no, that's an important point. That was hidden in the complexity, but it's absolutely there. Yeah, beaming and Doppler boosting, and to some extent the ray tracing. That all has to be done numerically, and in the actual fits, that was all. Of course, that was what Andy, my student, implemented, and what I showed was simply the Newtonian case, just for the purposes of making the approach more transparent and simple. But in reality, it's not easy to keep track of. It's not that it's particularly hard. It's a lot of work to keep track of exactly the effects that you're describing, Doppler boosting, and the ray tracing, and the in general the photon kinematics.
Right. Yeah.
Thank you.
Thank you.
Is there still some question? No, so thank you again, Professor Berbis, for your talk.
Thank you.
Normally, our next speaker is Dr. Franco Giovanelli, but I'm not sure if he's here. I didn't see it in the list. See him in the list.
Modified Landau equation. So this work is mainly from the publication in here in Binaries, recent published recently, and part of this work is also from ABJ, which where the work is got accepted for publication and supposed to appear in the archive by tomorrow. And this work is done with my supervisor Bani Brata. So observational evidences say that accretion disks are turbulent, though they are relativistical. By relativistical, it means if we consider a local fluid particle in the Keplerian accretion flow, for example here, then if we perturb this flow, this fluid particle, what will happen that the perturbation will not grow, they will decay. Hence the flow is stable. So the question is how come these this accretion flow become turbulent? Is there any instability mechanism through which the nonlinearity and hence turbulence will come? To answer that, there is magnetic rotational instability proposed by Balbus and Howley in 1991 following Velikov and Chandrasekhar. So, particularly for hot flows. So how does this magnetic rotational instability work? Is like due to the coupling between magnetic field and rotation, a spring mass analog is established. So due to this coupling, it looks like a spring is attached with the two particle, and due to the perturbation as this spring elongated, tensional or restoring force generated, and because of this restoring force, the torque generates in the inner particle and the outer particle. As a result, the inner particle falls in and outer particle goes out with the extra angular momentum. Hence, this runaway process goes on, and the angular momentum goes out and particle falls in. So this is how MRI works typically. Now, MRI has been quite successful in describing the various accretion phenomenon. However, it is not out of caveats. For example, protoplanetary disk where the ionization is smaller beyond certain toroidal magnetic field, it gets suppressed. When the magnetic field is stronger, it ceases to work. So in all these cases, there are of course different mechanisms for different for particular cases to bring the nonlinearity and hence turbulence into the system. But our venture is to look for more general mechanism with which we can bring the nonlinearity into the system, and hence which lead to the turbulence. So that is why we look for a linear instability from hydrodynamical point of view to explain the turbulence. To do so, lately the effect of an extra force which is stochastic in nature has been explored in the Navier-Stokes equation, which describes the local local flow, in the linear perturbation to explain the underlying instability that could further give rise to turbulence. Now, how do we know whether these perturbations grow or not? So with which equation this amplitude of this perturbation changes with time, that is the evolution equation of perturbation, is called Landau equation. Here we saw that in the presence of extra force, this Landau equation gets modified from the previous one, that is where there is no extra force. And this, what is the implication of this modification to the accretion physics, that is also that will also discuss. Now with this we talk about the extra force. So the question arises, what could be the plausible origin of extra force? For example, we can have fewer origins like the accretion, the interaction between the dust grain and fluid parcel in protoplanetary disk. Also, the feedback from outflows and jets onto the disk, etc. Now, having said that, let's formulate the problem. To do so, we go to a local region in the accretion disk where we consider a Cartesian box, which is shown in here in figure, and to incorporate the rotation at that particular radius in the accretion disk, we rotate the box along this in this radius throughout the accretion disk. As there is a differential rotation in the accretion disk, so in the local box there will be shear in the background flow. So we perturb this shear background flow and see what happens to the perturbation with respect to the time. Now, in that frame, in that local box, we describe the fluid motion with the Navier-Stokes equation, but in a recursive form. We recurse the Navier-Stokes equation by eliminating pressure term, as we are dealing with the incompressible flow, and the ultimate. So this recursed Navier-Stokes equation is called the Orr-Sommerfeld and square equation in presence of extra force and co-release force with the nonlinear term intact. So these two are the nonlinear term, and these are the contribution from the extra force. Now, if we get rid of this extra forcing and nonlinear forcing, the rest equations were considered to describe the transient growth for linear shear flow by Mukhopadhyay, Absurdin, Narayan. Now we solve these equations with the boundary conditions, no slip boundary conditions, where this capital U is the background shear flow, and the small u and zeta are the x component of velocity and vorticity perturbations, and q is the rotation parameter, which is 1.5 for Keplerian flow, and the typical angular frequency profile in the Keplerian region is described here, where r subscript r describes for an arbitrary radius, and subscript 0 describe a reference radius. Now, if we consider the linear theory, we get rid of these nonlinear terms, and we recurse those two equations into more concrete form, where this q is described as here. The more general solution, u and zeta, have 4 variables x, y, z, and t. As there is shear along x direction, we cannot consider Fourier solutions, but along y and z direction, as these are free, so we consider Fourier solutions along y and z direction. So this k wave vector is along two direction y and z, and also this r position vector is also along 2 direction y and z. We solve x numerically. This L is the is operator which is described, the 4 elements of which is described below, and this gamma which contains the information about the extra forcing is described here. Now we consider the trial solution to this equation as shown here, where a is constant and qx is the eigenfunction of this homogeneous equation, that is neglecting or without this extra forcing. Now, if we solve this homogeneous equation, we will have eigenvalue and eigenfunction equation. So this sigma is the eigenvalue of this homogeneous equation, and according to our convention, if the real part of this if the imaginary part of this sigma is positive, then the solution will grow, hence the flow is unstable, and if imaginary part of sigma is negative, then solution will decay, hence the flow is stable. Now, with this information, we plot the eigenspectra for 3 different flows with the parameters shown for Reynolds number 2000 and KYKZ1. KYKZ are the z, y and z component of wave vector. So for Keplerian flow, and for constant angular momentum flow, and for plane quake flow, that is linear shear flow where there is no rotation, we see that all the eigenvalues are well below 0, that is they are all negative, hence the flows are stable. Now, please remember this. Keep in mind this red box eigenvalue, which are the closest to 0. That is, they are called the least stable eigenvalue. Now, to develop the perturbation evolution equation, we have to get to the nonlinear theory. So, the nonlinear solution are shown like this. Now, for the first order, for weak nonlinear theory, for the first order, we consider n equals to 1 only, and hence we will obtain this equation where Q1 is like this, which we are supposed to get, where Qx is the eigenfunction for the linear solution, linear homogeneous equation, and AT. In the linear case, these time dependence were exponential, but here we do not know. So we will get the evolution equation of AT, which is the Landau equation. So we substitute this equation 4 in equation 3, and we will obtain this equation. This is the modified version of Landau equation. The modification occurs in this script n. Without this term, this is usual Landau equation. For 2 dimension and 3 dimension, these are derived by Ellingson et al. And Rajesh respectively. Now, n contains the information of this extra forcing, this gamma prime, which relates to the extra forcing like this, shown in equation 6. And this P contains the information of nonlinearity through S. Now, let's look at the variation of n, which modifies the Landau equation. It shows that beyond certain time, this script n gets saturated, and this saturation value, this saturation increases as we increase the Reynolds number for a particular extra force. And if we check the variation of sigma I with respect to Reynolds number, for your information, this sigma I, these black dots are these red boxed in the eigen spectra. That is the each black dot corresponds to the least stable eigen value corresponding to the Reynolds number. So we see that as Reynolds number increases, the sigma I approaches 0 here. Now let's look at the evolution of AT, that is the amplitude evolution of in the linear regime. So here we see along the y-axis, this is the modulus of amplitude, and along x-axis it is the time. We see that in 3 sets, each 3 sets represent different forcing. Here 10 to the 2, here 10 to the 4, here 10 to the 6, and each set, the different color represents the different Reynolds number. We see that beyond certain time, this amplitude gets saturated. So this saturation also has scaling with the noise as linearly. So this saturation scales with the noise linearly in the and the saturated value, at which value this AT gets saturated beyond certain time, is this one. So the saturated value is given by this. Whatever be the initial condition, they will always approach this value. Now, I showed earlier that as Reynolds number increases, script n increases, and the sigma I, modulus of sigma I decreases. So in principle, we can have, for very large Reynolds number, which is applicable for accretion disk, that this sigma I is very, very small. The magnitude of the sigma I is very, very small. So in for smaller gamma, that is for irrespective of this n also, this AT can be in the nonlinear regime. Hence, this saturated value from here, what we get because of the large Reynolds number can be in a nonlinear regime. So this system could be in the nonlinear regime, depending on Reynolds number and gamma. Now this was the linear study. Now in the nonlinear regime, what happens is that if we neglect the extra forcing, this black and green curve, this green curve and black curve, what we see that depending on the initial amplitude, beyond certain value of the initial amplitude, if the amplitude is larger beyond certain value, then it diverges, the amplitude diverges, otherwise it decays down. But it is not the case for where the forcing is there. So if it is a non-zero, then beyond a finite time, depending on gamma, it diverges. And it also does not depend on the initial condition, rather it depends on the extra forcing values. So having all this information, let's conclude and get some conclusion out of this information. So if this equation 9 is the usual Landau equation without forcing, where AL is the amplitude of the nonlinear perturbation, and K1 is related to growth rate, and K2 related to the nonlinearity, contribution from the nonlinearity. Now, if K1 is positive, that is growth rate is positive, and K2 is negative, then this amplitude saturate at a large time, irrespective of initial condition. That we get in our case in the linear regime, where this equation described in the nonlinear regime. If both K1 and K2 are positive, then AL, this amplitude diverges beyond certain time. We also obtain the similar kind of evolution of AT in the nonlinear regime, but that depends upon the initial amplitude. That does not depend on the initial amplitude. That in our case, it depends on Reynolds number and gamma, the extra forcing. So we can say that, we can conclude that although in shear flow without forcing, K1 is negative, but the very presence of the forcing makes it effectively positive. Hence, with this positive, effectively positive sigma I or K1, the system is in the nonlinear regime. Hence, this nonlinearity in the system could further bring turbulence into the system. These are the references, and thank you.
Thank you very much for your good, interesting talk. Is there any question? So I just remind that you can do it in the chat, or you can write, you can do it by using the reaction and raising your hand. Okay, so if there is no question, we're going to thank you again, Subham.
Okay. So I'm stop sharing.
Yes, please. So we are really good on the schedule, so that's really, really nice. Eva, are you there?
Yes, I just came in.
Okay. Super.
Hi.
Okay, so then our next speaker is Eva Hackman. She's going to talk about electromagnetic field in polished Donnet models.
Okay. Can you hear me and see the slides?
Yeah.
Good. Very good. Okay. I will talk about today about a topic which is related to what Professor Stuchlik presented this morning, namely electromagnetic fields in Polish donut models or geometrically sick tori. And I have to mention that this, what I'm presenting you is work in collaboration, and actually the two who did the most of the work, most of the calculations, are Chris Schroven and Audrey Trover. And the other collaborators are Klaus Lemmerzal, Vladimir Karas, Jiri Kovan, Peter Slani. Okay, so this is the plan of my talk. I will first give you some motivation why we are looking into this. Then I will talk about equilibrium configuration of charged fluids and give you some examples that we constructed. And then I will summarize and discuss. So, okay, let me give you some motivation. So, what is really nice about black holes is that in a certain sense, they are very simple objects. So they are just described by only 3 parameters, as stated in the O'Hare theorem. And this is the mass, the angular momentum, and the charge. Electric and actually also magnetic charge, but this is, yeah, not so relevant actually. So, and in astrophysics, usually we also neglect the electric charge of the black hole. And there's, of course, a reason for that. And the reason is that the gravitational force is much, much weaker than the electromagnetic force. And this means that if you have some charged black hole, then it will accrete oppositely charged particles from its environment and thereby decrease its net electric charge very quickly, actually, to very tiny values. And you can see here this charge parameter Q, which is related to SI units here, to the charge to mass ratio, actually. And this should be below 10 to minus 18 in such a setting. But then you could say, okay, so what if you have a really isolated black hole, no environment to accrete from or whatever? Even then, in complete vacuum, you will have pair production. And even then, this charge to mass ratio will decrease quickly to values below 10 to minus 5. Okay, so is there at all some, say, mechanism where charged black holes may be relevant in astrophysics? So, of course, black holes are usually not isolated. We have a lot of things going on around them. And in particular, we have electromagnetic fields in their vicinity, for example, from the accretion disk or also from the galactic field or from other stars nearby, say magnetars or whatever. And the rotation of the black hole will interact with these electromagnetic fields. And due to this interaction, you can have actually some stable net electric charge of a Kerr black hole, say, or then Kerr-Newman black hole. And there is a famous example where you have an asymptotically uniform magnetic field that was calculated by Wald in the 70s. And he showed that then there would be a stable net electric charge, which is proportional to B, to AB. Okay, so this actually means that astrophysical black holes should have a non-vanishing charge, but it should be very tiny. It should be many orders of magnitude below unity. And there was rather recently an estimate for the charge of Sagittarius A star by Sajajek et al. In 2018. And this was based on the observation of Bremsstrahlung. And they showed that the charge of the supermassive black hole at our Milky Way should be below 3 times 10 to 8 Coulomb, or converted to our dimensionless charge to mass ratio here, it should be below 4 times 10 to minus 19. So it seems that this number here is somehow, say, a realistic assumption for the electric charge of a supermassive black hole. Okay, so if this charge to mass ratio is so very small, then we can very safely neglect the influence of the charge on the space-time geometry. It will be very, very small. But we can turn around the argument that we had before and say, okay, but the electromagnetic interaction is much stronger than the gravitational one. So is there some influence of the charge of the black hole on charged particles or on charged fluids in the vicinity of it? And you can do a very quick order of magnitude estimate. For example, you take a Kerr-Newman black hole with, say, this somehow realistic assumption here for the charge. And then you take a look at the equations of motion of charged particles, and you find that they contain this product here, where this little q here is the charge to mass ratio of the particle. And if you assume that you have some elementary particle, a free electron, for example, then this is actually very huge, this small q here. And also for free protons, of course, 3 orders of magnitude lower to the higher mass, due to the higher mass. But this makes this product here, even though this capital Q is very, very small, actually this puts it into a range where you would not say from the very beginning that this is completely negligible. So from this quick order of magnitude estimate, it seems that it makes actually sense to include the charge of the black hole as soon as you consider charged particles or charged fluids in the vicinity of the black hole. And this was our motivation to look at this particular setup. So what we took was a geometrically thick accretion disk, also called polished donut. And you see a sketch of it here on the left side. So these are like equi-pressure surfaces that you see here. And on the right, you have a comparison to the time average numerical simulation. And this was actually created by Abramovich, this figure. So the original model of this was developed by Abramovich and co-authors in '78 in a Kerr background. And because you have a Kerr background, you have 2 killing vectors, a time-like one and azimuthal one, giving you conservation of energy and angular momentum. And this model is very heavily relying on the assumption that you have only circular motion. So you can model the force velocity of the fluid that you're considering just like this here. So you have a UT component, and then you have these 2 killing vectors. So you have only a UT and a U phi component in your force velocity. And this omega here is the angular velocity UT over U phi. And just as a side remark, if you have circular motion, you can look at the effective potential for geodesic motion, and you can find that these pressure maxima here, where the pressure gradient vanishes, so here at the center and at the cusp, you actually find that this is on geodesics. This moves on the geodesic trajectory, and you can nicely derive the conditions for that from the effective potential and find the center and the cusp of the polished donuts. Okay, so if we have some charge of the black hole and some charged fluids around, is there some significant influence? And of course, we were not the first to introduce some charge or electromagnetic fields into the picture. First was probably Komisarov, who introduced a toroidal magnetic field that is attached to the fluid into the game. Later in 2011, there were Kova et al. Who introduced charged fluid in the Reisner-Nordstrom background, so charged Schwarzschild spacetime. And later on, he and his co-authors also introduced external electromagnetic fields like a uniform magnetic field or whatever into this picture. But in these papers here, they restricted to static spacetimes. And we were really interested in what happens if we introduce the rotation into this game, because this should, of course, be very important and significant. So the first observation that you can make, and this was also mentioned by Professor Stuchlik this morning. So if you want to do some ideal MHD considerations, then you need to check some conditions. So first we need to assume that the electromagnetic field tensor F shares the same symmetry as the spacetime. So you can say there should be some potential, and this potential should only have an AT component and an IA phi component. So this is what is written here as phi and theta, so which is related to the two killing vectors. So then if you do ideal MHD, you need that this condition here is fulfilled. So, and this in turn implies that you need to satisfy this equation. And then this was already considered in 1993 by Bonazzola et al. And they showed that this can only be satisfied if either the omega, the angular velocity, is constant, or if your A phi component is a function of your angular velocity. And if you follow this approach further, then you find that you have also this relation between the electromagnetic, the components of the electromagnetic potential. And this is somehow not what we wanted to do, because we wanted to have some electromagnetic fields that are external to the fluid, so generated by the black hole or by some external magnetic fields. So this is not compatible with these assumptions here. So if we want to do this kind of considerations, we have necessarily to assume a finite conductivity. Okay, so these are then the basic equations that we need: energy conservation, Maxwell's equation, and the charge current equation. And then from this we can derive an equation for the pressure. You probably recognize this part here. This is just the usual Polish donut equation. And then you get two terms that are introduced by considering the electromagnetic interactions. And now, of course, we have to check this equation for consistency. So we assumed from the very beginning that we have a stationary model and an axially symmetric model. So we need that these derivatives here with respect to time and azimuthal angle become 0. So this is trivially satisfied for the first two terms here from the usual Polish donut model. And this is also fine for this, but the last term here gives you some troubles. And this this term here has to vanish for mu equal to T and phi. And this, so say the simplest possibility to do that is to put sigma to 0. You can do some slightly more general things, but the resulting equations will be the same. So you can have some, say, direction-dependent conductivities or so on. But this is, I would say, equally special. So for the time being, we put the sigma equal to 0 so that this last term here vanishes. And this is exactly the same approximation that also Professor Stuckling mentioned this morning in his talk, which is quite of the opposite of the, say, ideal MHD case. Okay, so this term goes away. Then we have the integrability condition written down here. So we know from the Polish donuts that we need some kind of equation of state for that, and the von Cipes theorem stating that we need either that omega is equal to constant or L is equal to constant, or that they are related by some kind of function. Okay, and then, but in addition, we have to deal again with this electromagnetic term, and this integrability condition means that we need to express this term here like this here. So in terms of, basically in terms of a gradient of some function S. And this is actually most of the time the hardest part in constructing these models. It can be easily done if you assume that omega is constant, but this is rather special in a sense because we know that for Polish donuts, omega equal to constant does not give us some bound structures. You can also do some other things. I will go into this more detail when I present you the examples. Okay, if you succeed to do that, then you have this kind of equation here, and this you can then integrate rather easily. And you can find bound structures if your pressure has some local maximum somewhere. Okay, so, and we then went on and constructed some examples in this kind of setup. So first we took a rotating black hole that gives us a gravitational field, because we know that the charge of the black hole should not significantly influence the space-time geometry. So then we have an asymptotically uniform magnetic test field. So we also assumed that this magnetic field is not strong enough to influence the space-time geometry. And we assume that it is aligned with the rotation axis. So this is a classical wall solution. And if you have such a uniform magnetic field, then we know that it induces a test electric field of the black hole also, which is proportional to the strength of the magnetic field. And for this first example, we assume that we have some rigid rotation actually. So to have omega equal to constant, to be able to construct this, this scalar function S, this gradient. And we know that it is impossible for the uncharged cage to find bound structures for this assumption here. But if you go to this charged fluids, then we actually found bound structures, equilibrium configurations, and we found them both on the equator, which is the usual torus-like solution, but also on the polar axis. And this is something that Professor Stucklik also mentioned this morning already. And here you see two examples, how this could look like. So here you see typical polished donut solution. We have here some closed torus with a cusp where you have the accretion process. And then on the right here, you see some what we call a polar cloud. So you have this clouds that hover above and below the black hole, centered on the rotation axis, and they rotate rigidly at this axis. Okay, and we were interested, what are actually the conditions for these polar clouds to form? So we considered some special subcases of our setup. On the one hand, we put the electric charge to 0. On the other hand, we put the magnetic field to 0. And in both cases, we found polar cloud configurations. So we concluded from that from the three parameters, spin of the black hole, electric charge of the black hole, and this magnetic field, you need 2 to be non-zero to have this polar cloud configurations. So the last point where A is equal to 0 and you have Q and B, this was already discussed in 2014 in this paper here. So you need 2 out of these 3 parameters to have this polar cloud solutions. We also looked at dipole magnetic fields, more or less the same setup, but replaced the uniform, asymptotically uniform field by dipole field, with rigid rotation. And again, we found this, this torus-like solutions and this polar cloud-like solutions. And last but not least, we also discussed, so we also wanted to have some non-constant, some non-rigid rotating tori solution, which are also somehow more physically realistic. But that we couldn't manage to do with a rotating black hole. This was too, so we did not succeed to find this scalar function S that we need. But for a non-rotating black hole, we succeed to assume L equal to constant and still construct this scalar function, which looks a bit more complicated. You see it here, so it's a derivative of it. And for this case, we also found, of course, the usual polished donut-like solutions, but also something which is somehow strange and interesting, but maybe also not too physically realistic. We found also some double tori on the equator. And here you see an example of that. So you could have some double torus that are either separated or that they are connected by a cusp. But please note that you do, for this type of solution, you do not have the possibility to have a cusp here to enable accretion onto the black hole. And this is why we think it might not be actually very, very realistic. And here on the right, you see a typical example of a usual polished donut solution. Here you could also have some kind of cusp involved. Okay, I think time is running short, so let me summarize. I hope I could convince you that astrophysical black holes actually should have some very tiny but non-vanishing electric charge that should be below this value, maybe in 1 order or 2 orders of magnitude lower. In this case, influence on the space-time geometry is totally negligible, but you should maybe not assume from the very beginning that the influence on charged matter is non-negligible or is negligible. So we discussed some charged fluid solutions in equilibrium, and we found that these charged black holes basically enable rigidly rotating tori, and that we could construct this rigidly rotating polar clouds if you have from A, B, and Q 2 non-vanishing parameters. So say spin and magnetic field, or spin and electric field, or only magnetic and electric field. And you can also have this rather kind of strange solutions of the double tori if you go to the constant angular momentum but static case. Okay, then let me close with a short discussion. We are, of course, totally aware that this is some kind of toy model that we were considering here. So in particular, what is troubling us is this vanishing conductivity assumption, which makes it only applicable to, say, very special settings. But nevertheless, we think it could be interesting to check this charge effects in more realistic models, say. So something where you have maybe small conductivity, or maybe you can do some analytical perturbative treatment or so on. Okay, so we are planning to investigate this in more detail, but so far you can find more details on that in these 3 publications. Thank you very much.
Thank you, Eva, for a very nice talk. Okay, so there is some question. Yes, Mukesh Kaivyas.
Yes, I missed some part of this talk, so I may have missed the answer already. So if a stellar mass black hole is charged and it has an accretion disk, what effect do you expect on the plasma which is nearby rotating?
Well, I think it depends on the plasma that you have. So if this is somehow highly charged, I would expect that you have maybe some noticeable effects just due to the usual, say, EM interaction. So, well, so it should be if you. I think you should see something if you have a dilute plasma, which is not very heavy, say, and which is highly charged. Then there is maybe a chance to see something, I guess. But so you need to have a high charge to mass ratio to get something out of it. Does this answer your question?
Yeah, we see the spectrum from Keplerian disks where the high temperature portion comes from a nearby region in the accretion disk, which is roughly around 3 or 4, a few Schwarzschild radius. So if it has an impact, then we can expect something to be seen in the spectrum.
Well, I mean, there should be several things. For example, the ISCO should change, for example, so it could have an effect on the inner edge of the disk. For example, I would expect that it should come closer than you would expect for a neutral mass or matter orbiting. So this would maybe be the most, I guess, prominent effect that you could expect, I guess.
All right, thanks.
Okay, there is some question in the chat. So maybe can you see them? Yeah.
Yes, I can
Tan.
see. Yes, yes. Well, any observational evidence? So I think actually no, because well, as I said, we had this vanishing conductivity assumption, and I think so. At least I'm not aware of any observational evidence, but well, I'm not from the observations, so I can actually not say too much about it. But I don't think so. And there was a second question by Daniela, I think.
Yeah, but I mean, maybe we can, because we're a little bit
yeah, I
right
can
on
answer
time.
it in this. I can answer.
Yeah,
it in
so
the chat.
maybe
Yeah.
yes, we can, or in the chat, or maybe after at the
Yeah.
end when we will have a little bit more time.
Yeah, sure.
Okay, super. So thank you again, Hiva. We will go to the next talk. So the next speaker is Sudab Rajan Datta. He will discuss about advective accretion onto non-spherical accretor in wide dwarf and neutron star binaries.
Hello.
Hello.
Are you able to hear me? Yeah.
Yeah, we can hear you.
Are you able to? Oh, thank you. So I'm starting this thing soon. Are you able to see my presentation?
Yes.
Okay. It is in right orientation and everything is correct.
Yeah, the orientation is fine.
Okay, thank you. So I'm going to present. I'm Sudev, an Indian Institute of Science, Bangalore, and I have done this work in collaboration with Prashun and Bhupendra. So this work is advective accretion onto a non-spherical accretor in white dwarf and neutron star binaries. So if the central accretor is deformed from spherical to non-spherical, then is there any effect we can expect in the accretion disk? This is the expression of this work. So first, coming to motivation, so it is very natural that stellar rotation or presence of magnetic field or the for the continuous accretion going to the central accretor can make the accretor to spherical to non-spherical. So for spherical eccentricity is 0, and for non-spherical it will tend to 1 gradually as it becomes oblate type. And another motivation is Mishra and Boydto already explored that this non-spherical nature of the central accretor gives effect in the if the disk is optically thick Sakurashina disk, then you can see from the plot that there is a from the non-sphericality, and if the eccentricity is changed, then the spectra from the accretion disk is also changed. So from this motivation, we are exploring that we are expecting that also there will be a change if the effect of non-sphericality is included on the dynamics of advective hot accretion. So this work explores that if the central accretor becomes non-spherical, then what is the effect on hot advective accretion? So coming to formalism part, we are simply solving the mass continuity and radial momentum balance equation in where the effect of the non-spherical accretor is coming through the gravitational force Fr, which is the gravitational force attracting by the central accretor. And here E is the eccentricity of the accretor. So E is large, means it is more oblate, and A is the semi-major axis of the accretor. Rho star is its density, which we have assumed uniform throughout our work. Now we do all this analysis in the dimensionless form. So if we convert the force term in dimensionless form, then it becomes that this expression. So you can see that this depends only on AE. So multiplication of AE, same major axis and the eccentricity. So separately they don't affect the result. Only the multiplication of A and E value affects the result in our work. So a rearrangement of all the equations leads to this dVdr expression, slope of the radial velocity. So now we do the standard critical point analysis and solve the problem as initial value problem. So here the free parameters in our formalism lies the specific angular momentum of the flow, the energy of the flow, and as well as A into E, as I have described in the last slide. A into E is coming from the effect of the central activity. Now going to the results. So now coming to, there is a critical, so we have done the critical point analysis. So we start that from that point and do solve the dynamics. So starting from the location of the critical point. So as we are considering the inviscid flow, there is no dissipation. So the angular momentum as well as energy of the flow remains constant for the disk. So which is quite simplistic, but we are doing this in this preliminary study. And so we can estimate many things from the EC versus RC curve. So what EC and RC are? EC and RC are the energy of the flow at critical point, and RC is the location of the critical point. So you can see that the left panel is the for neutron star. As you can see that A into E is the 3.0. So where A is 6 Rg and E is kept at 0.5, and here same thing, A is 3540, which is for white dwarf. So now we can see that EC versus curves changes with the variation of the angular momentum of the flow. So now you can see that X type and O type, there are different types of critical points, X type and O type critical points. So for the time being, we can assume that the X type critical points are responsible for the successful accretion. And if there is O type critical point, so there will be no accretion, and matter will go back and will not be accreted to the central accretion. So for successful accretion, we require X type critical point. It is coming, and it is estimated the X type, the nature of the critical point comes from the slope value of the radial velocity. So here you can see that X type critical point and the number of X type critical points determines that whether there is any possibility of shock or not in the flow. So we can see that X type critical point varies, number of X type critical point varies with L, and for a specific parameter space regime, we can get the presence of 2 X type critical points in the flow. And so existence of multiple X type critical points leads to the possibility of existence of shock. And so we find that here we can get, there is a possibility to get the shock. And here we are exploring the Maclaurin spheroid, using Maclaurin spheroid potential, not any general relativistic effect in this. So within the the beauty of the Maclaurin spheroid potential is that within the Newtonian regime event, we can get the presence of shock, which was not possible earlier within the advective flow. So here you can see that the curve changes with the parameters value related to the accretor. So also we can see that AE value changes, and the presence of X type critical point and location changes. So sorry, one thing I forgot to mention, the straight line, the straight horizontal line indicates the energy of the flow. So if the straight horizontal line where cuts the curve, that indicates the location of the critical point, and through that point the matter will be accreted. So here this curve shows the variation of AE also leads to the variation in the RC curve, and as well as the number of X type critical points varies, and as well as the probability of shock also varies. So now, as we are within Newtonian regime and not considering any general relativistic effect, so we focus on the results for white dwarf only. And similar result we get for neutron star also, but without general relativistic effect, those are not too robust. Now, as we find the shock is possible, now we are exploring that when the shock is probable more and when less. So we can estimate the probability of the shock from the swallowtail diagram. So this diagram presents the y-axis is the EC, energy at critical point, and x-axis is the entropy at critical point. So this mu c indicates the information of entropy. Now, this shock we are considering is Rankine-Huvonier shock, and the necessary condition for this shock is the increment of entropy. So from the increment of entropy, we can estimate that the shock is how much probable. Now here O line, this O line indicates the outer branch, outer critical branch, and I line indicates the inner critical branch. As we have seen that two X-type critical points are present, so we can give the inner one, inner X1 is the inner critical point, and outer X is the outer critical point. So through these 2 points, a successful accretion can happen. Now this region, you can see that ABD region. So this ABD region presents the probability of the shock, because the entropy has to increase, so the flow has to jump from O line to I line, and keeping the energy constant. So this ABD region increases, and so it indicates that the probability of shock also increases. So higher range of energy value is available for making the shock. And you can see that with decreasing eccentricity of the central accretor, gradually the probability of the shock increases. But again, with decrement of too much, the inner critical point vanishes, and as well as shock cannot happen. So we can conclude that within a limit, decreasing eccentricity increases the probability of the shock. Now we can also keep in mind one thing, that for all these things, we keep the specific angular momentum of the flow constant, specific angular momentum as well as energy of the flow constant. Now, as we have seen the probability of shock, now coming to the location of shock. So how can we get the location of shock? There are other conservation equations, conservation of mass and conservation of energy across the shock location, which leads to the shock invariant quantity. Means with shock happens, both sides of the shock, this quantity should remain same, and it is coming from the conservation equation. So this plus sign indicates the after the shock, and minus sign denotes the before the shock. So after this quantity we can calculate for outer branch as well as inner branch. So we have calculated for outer branch as well as inner branch, and then we see that they are intersecting at 2 points, A and B. So for successful accretion and shock solution, this shock invariant quantity should remain constant, and these 2 points can be the possible location of the shock. But from the perturbation analysis, we know that this inner one, that A point, is unstable point. So that is why this B point is our desirable shock location. Now coming to the hydrodynamics around white dwarf. So we see that different parameter regimes can give rise to a shock, and different parameter regimes cannot give rise to shock. So we have seen that we have shown here, the left one is the Mach number plot and the right one is the sound speed plot. So we can see that for a particular parameter space, shock happens, which shows the sharp jump in the Mach number as well as sound speed. And for other parameter space, a shock does not happen and the flow accreted smoothly. So from the shock, we can see that if shock happens, then the velocity decreases and the sound speed increases. So this leads to the density increment, because the mass continue, because the accretion rate remains constant. So as velocity decreases, so density increases in the post-shock region. And as you can see that sound speed increases, it indicates that temperature also increases in the post-shock region. Now, what we can see, that particular parameter space is giving rise to a particular shock only. So here we have give the typical set of values of parameters. So A is fixed to for neutron star 6 Rg, and white dwarf is 5900 Rg, and eccentricity is fixed to 0.5 and 0.6. So when eccentricity is fixed and LC is the angular momentum and EC is the energy. So when eccentricity and LC is fixed, then for a particular range of energy value we can give rise shock, and vice versa. Similarly for the white dwarf we can see. So a range of eccentricity LC and EC can give rise shock when we fix the others. Now, if we vary all the three, then we can see that for eccentricity value from 0.2 to 1, we can get the shock solution with adjusting the angular momentum and energy value. If we decreasing the eccentricity, then we have to decrease the angular momentum value also to get the shock solution. Means we require the more sub-Keplerian flow if shock solution to happen. Now, coming to the observational support, that is it possible physically in the observation that shock can happen when the accreting to the non-magnetic white dwarf? Non-magnetic, because we are saying that because we are mentioning the shock solution within the advective flow, so disk must be present, and if the magnetic field is too strong, then disk will be distorted and channel flow will be there. So the only viable option for the deformation is the rotation and continuous accretion. So rotation we can explore, and we can see that from the observation, they have reported that non-magnetic characteristic variables spin frequency lies within 0.2 to 0.3 Keplerian spin frequency. And we, from the Maclaurin's Farad expression of Chandrasekhar, we can get that this rotation is sufficient to generate the eccentricity for 0.2 to 0.4 value. So, and we are able to get the shock solutions for 0.2 to 1 within eccentricity range. So it might be possible. And another observational support that is emerging significantly nowadays, that the optically thin hard X-rays observed from the non-magnetic lattice-spacing variables in high states as well as in quiescent states. So it indicates that the hot advective flows are present around non-magnetic white dwarf. So, so for our validity of our result, the hot advective flows are present around the non-magnetic white dwarf, as well as it can be deformed to such eccentric value. So we can conclude that it is not very unusual for the occurrence of shock within advective flows onto a non-spherical, non-magnetic white dwarf accretion. Now, giving summary of the talk, so treating compact object as a Maclaurin spheroid opens a new possibility for the formation of shock, because earlier people used to realize this kind of shock when general relativistic effect is included in the flow, or the due to the presence of the hard surface of the accretor. Now, what we found that if the accretor becomes non-spherical, then also without considering any general relativistic effect or the hard surface, the shock can happen within the advective flow. And as far as we are concerned, understand the flow hydrodynamics around the non-magnetic characteristic variables. So our findings are robust because we don't consider any general relativistic effect. And white dwarf accretion around white dwarf hardly deviates from Newtonian regime. And finally, some observational features, for example, high significance of fitting the spectra with multi-temperature plasma models rather than single temperature. Why we are saying? Because that if shock happens, then the temperature difference within the flow becomes more prominent. Because shock solution gives the steep increase within the steep increase of temperature and density within the flow. And there will be a certain discrepancy difference in the density and temperature than pre-shock and post-shock. So then there will be much higher requirement to fit the data with multi-temperature component than single component. And another thing, and the observation showed the variable X-ray efficiency for different sources. So X-ray luminosity of X-ray ratio of luminosity X-ray by luminosity of UV varies across the sources. That also can be explained if the shock is present or shock is not present for some sources and some not. So this is thank you for your kind attention.
Thank you very much for your nice talk. Is there some question? We have time, so please don't hesitate to ask. the speakers. Yeah, so we have one, Mukesh Kavyas.
Yeah, it looks an interesting concept. So I would like to ask you, what if the star is pulsating? In that case, E will be changing with time. So do you expect something interesting to happen there?
If the star is pulsating, then it is rotating, obviously.
So in that case, this E, which will not be constant
Yeah.
in time. So do you expect something more?
Yeah, exactly. Exactly. Yeah, I think that possibly there will be change in the accretion disk due to the eccentricity effect for that, because E will change at that time due to its rotation.
Okay.
Is there any other question? Okay, so I think we can thank you again, Sudeb.
Yeah, thank you. I'm stopping here.
Yeah. Okay, super. So we are going to the last talk of the session. Oh, sorry. Okay.
Yes,
so yeah, you're here. So the last talk of our really great session will be Shogufe Varaji. She will discuss about magnetized accretion disk structure in the background of an accelerating black hole. So please, Shogufe.
Yes, I try to share first. Please.
Yeah. We have time. Take your time.
Okay. Do you see the slides?
Yes, that's perfectly fine.
Okay. First, let me say thank you for being in the very last talk of the session. Today, I'll be sharing with you an overview of the disk structure around the uniformly accelerating black hole. I divided my presentation into 4 parts. I'll start off by providing motivation of the work. Then I'll go to a step briefly magnetized tori model. Then I continue by briefly explain about the space-time, and at the end, some results and summary. Also, I should mention that this is a joint work with Audrey Tova. Okay, about the motivation. Of course, understanding the nature and hidden properties of solution to Einstein equation could be one of the important tasks.